Close your eyes for a moment and picture a universe without light, not just the darkness of a moonless night, but a profound and absolute blackness that stretches across the entirety of existence. There are no stars, no galaxies, not even a single point of brilliance to pierce the endless void. For hundreds of millions of years after the Big Bang, this was the reality of our cosmos, a silent, shadowy realm known as the cosmic dark ages. It is a chapter of history so ancient, so fundamentally alien, that it challenges everything we see when we look up at the sky today. Yet, this is exactly where our story begins, a journey back to the very dawn of structure, to a time before the first light. What did the universe look like before the first stars and galaxies even ignited? This isn't just a philosophical question. It's one of the greatest detective stories in all of science, and we are on the verge of uncovering its secrets. We are about to dive into 30 of the most incredible theories that attempt to answer that very question. For decades, this era was a complete mystery, a blank spot on our cosmic timeline. But now, armed with data from powerful new telescopes like the James Webb Space Telescope and guided by brilliant theoretical models, we are finally beginning to piece together this ancient history. We are becoming cosmic detectives, sifting through the faintest whispers of light that have traveled for over 13 billion years to reach us. Each theory is a piece of evidence, a potential clue that brings us closer to understanding how our universe emerged from that formless darkness into the breathtaking tapestry of galaxies we observe today. This is not just about astronomy, it is a quest to understand our own ultimate origins, to trace the lineage of every atom in our bodies back to those first monumental fires. So prepare to explore the frontier of cosmic discovery. We will venture into ideas about the very first stars, monstrous beings that lived fast and died young, seeding the cosmos with the elements for everything to come. We will examine theories on how the first galaxies assembled themselves out of the primordial fog, and we will even consider some truly mind-bending possibilities, like the potential role of dark matter in sculpting the early universe. This is a story of colossal forces and delicate beginnings, a narrative written in the ancient light that we are only now learning to read. It is a journey to witness the universe's first sunrise, and by the end, your perspective on the night sky will be forever changed. Our journey into these 30 theories begins with one of the most foundational ideas, a concept that provided our first real blueprint for cosmic construction. This is the monolithic collapse model. Think of it as the universe's most ambitious building project, where an entire galaxy is erected in one fell swoop. To understand how this could happen, we need to rewind to that primordial soup we just imagined. After the Big Bang, the cosmos was an incredibly smooth, expanding cloud of hydrogen and helium gas. But it wasn't perfectly smooth, thanks to tiny quantum fluctuations that occurred in the universe's first fleeting moments. Some patches of this gas were ever so slightly denser than others. You could think of it like a vast, calm ocean with almost imperceptible ripples on its surface. In the monolithic collapse model, gravity seizes upon these tiny density ripples. Over millions of years, gravity acts as an amplifier, relentlessly pulling more and more gas toward these slightly denser spots. But there's a crucial player in this process that we can't see: dark matter. This mysterious substance, which far outweighs all the normal matter we know, began to clump together first. These clumps of dark matter formed an invisible gravitational skeleton, a deep well of attraction that the hydrogen and helium gas could not resist. The gas streams into these wells, and as it falls, it begins to spin and flatten, much like water swirling down a drain. This is not a gentle process, it is a violent, rapid collapse. Within a relatively short cosmic time, a massive, puffy cloud of gas directly transforms into a structured, rotating disk, a protogalaxy. This model paints a picture of elegant efficiency, where a single, giant cloud undergoes a monolithic transformation, giving birth to a galaxy in one continuous event. It's a straightforward and powerful idea, suggesting that the first galaxies could have formed quickly and magnificently, lighting up the dark ages with their brilliant newborn stars. This theory set the stage for all that followed, providing a clear and compelling starting point for our investigation into the universe's first structures. But while the monolithic idea offers a compelling image of cosmic creation, our understanding of the early universe took a dramatic turn with the development of a rival theory, one that is now considered the standard model of galaxy formation. This is the hierarchical clustering model, and it fundamentally flips the script on how structure emerges. Instead of a top-down approach where a giant cloud collapses into a galaxy, this model proposes a bottom-up assembly, a universe built from the ground up, piece by piece. It's the difference between constructing a cathedral in one grand gesture and patiently laying one brick at a time. The entire process hinges once again on the invisible scaffolding of dark matter. In the hierarchical model, the very first structures to form were not massive galaxy-sized clouds, but incredibly tiny clumps of dark matter. These are known as dark matter halos. Picture them not as solid objects, but as gravitational anchors, points in space where the pull of gravity is just a little bit stronger. In the early universe, countless numbers of these minuscule halos popped into existence, each one acting as a seed. Now imagine a gentle snowfall. A single snowflake is Chinese letter, Chinese letter, Chinese letter, Chinese letter, Chinese letter. But as it tumbles down, it collides with other snowflakes and they stick together, forming a small snowball. As that snowball rolls along, it gathers more and more snow, growing larger and larger with every rotation. This is the essence of hierarchical clustering. Those initial tiny dark matter halos were the cosmic snowflakes. Through gravity, they began to attract each other, merging together to form slightly larger halos. These mergers were not gentle encounters, they were violent collisions, but because dark matter doesn't interact with light or normal matter in any way other than gravity, these events happened silently in the dark. It was within these growing gravitational wells that the story of visible matter truly begins. The ordinary hydrogen and helium gas, which was spread throughout the universe, began to feel the pull of these merging dark matter halos. As the halos grew, they dragged vast reservoirs of gas along with them. When two halos merged, their associated gas clouds would smash together. This collision would compress the gas, and under the right conditions, that compression would trigger the ignition of the very first stars. So, instead of one giant burst of star formation creating a full-blown galaxy, the hierarchical model suggests that the first stars were born in small, isolated pockets within these modest halos. A galaxy wasn't born in a single event, it was built through a long history of mergers and acquisitions. A small halo with a few stars would merge with another, then another, steadily accumulating gas and stellar populations until a recognizable galaxy emerged. This theory is powerfully supported by the most sophisticated supercomputer simulations of the universe, which show this bottom-up process in stunning detail. These simulations, which model the gravitational dance of dark matter over billions of years, consistently produce an intricate cosmic web, a vast network of filaments connecting dense nodes with vast voids in between. This web-like structure matches almost perfectly with what we observe in the universe today. The hierarchical model elegantly explains why we see galaxies often grouped together in clusters and why the universe has a foamy, structured appearance. Most importantly for our quest to understand the first galaxies, this model makes a very specific prediction. The early universe should have been teeming with a vast population of small, faint, and incredibly ancient dwarf galaxies. These would have been the building blocks that, over cosmic time, merged to create the majestic spiral and elliptical galaxies we see today. Finding these primordial mini-galaxies is one of the primary missions of our newest telescopes, offering a direct glimpse into the universe's foundational construction phase. While the hierarchical model gives us a blueprint for how galaxies assembled, it leaves a crucial question unanswered. What was the spark that truly brought them to life? To find that, we must look not at the vast structures of dark matter, but at the individual power plants that ignited within them. This brings us to our third theory, which focuses on the celestial giants that lit the cosmic fuse, the very first stars known as population 3 stars. These were not just the first stars, they were a breed apart, unlike anything that exists in the universe today. Their existence and dramatic lives were the pivotal event that transformed the universe from a simple, dark place into the complex and chemically rich cosmos we inhabit. To understand why population 3 stars were so special, we need a quick lesson in stellar generations. Astronomers classify stars into populations based on their chemical makeup. Our own Sun is a population 1 star, meaning it's relatively metal-rich. Metals in astronomy means any element heavier than helium, everything from carbon and oxygen to iron and gold. These elements were forged inside previous generations of stars and scattered across space when those stars died. But rewind to the very beginning, and you find a universe made of only 3 things: hydrogen, helium, and a trace amount of lithium. There were no heavier elements, nothing to form planets, and certainly nothing to form life. This pristine environment is where population 3 stars were born. They were pure, composed of only the original ingredients of the Big Bang. This purity had a staggering consequence. It allowed these stars to grow to unimaginable sizes. In a modern gas cloud, elements like carbon and oxygen help the cloud cool down efficiently as it collapses. This cooling allows the cloud to fragment into many smaller clumps, leading to the birth of lots of small and medium-sized stars like our Sun. But the primordial gas of the early universe had no such cooling agents. It was much harder for it to lose heat. As a result, when a vast cloud of this pristine gas collapsed under gravity, it didn't fragment much. Instead, it funneled an enormous amount of material into a single, colossal object. Theorists believe population 3 stars could have been behemoths, ranging from several dozen to several hundred times the mass of our Sun. Picture a star so immense that it could contain our entire solar system within its diameter, a true titan of the cosmic dawn, and with great mass comes an incredible, ferocious power. These stars would have burned at temperatures far hotter than the Sun, shining with a brilliant bluish-white light that was tens of thousands of times more luminous. They lived fast and died young. While a star like our Sun will burn steadily for billions of years, a massive population 3 star would have exhausted its nuclear fuel in just a few million years, a mere cosmic blink of an eye. But their short lives were anything but quiet. Their intense ultraviolet radiation acted like a cosmic blowtorch, flooding the surrounding hydrogen gas with so much energy that it ripped electrons away from their atoms. This process, known as reionization, began to fundamentally change the very fabric of the universe, gradually transforming it from an opaque, neutral fog into the transparent, ionized expanse we see today. This was the universe's great clearing, and population 3 stars were the primary agents of change. Their deaths were as monumental as their lives. After a few million years, these stellar giants exhausted their nuclear fuel, and their cores collapsed, triggering cataclysmic supernova explosions of a scale we can scarcely comprehend. These were not ordinary supernova. Some models suggest they were so powerful they completely obliterated the star, leaving behind no black hole or neutron star, but scattering their entire contents far and wide into the void. In this final, violent act, population 3 stars achieved their most lasting legacy. They became the universe's first factories for heavy elements. The intense heat and pressure of their cores and their explosive deaths forged the first carbon, oxygen, iron, and gold. polluting the pristine gas around them with these newly created metals. This pollution was the most important step for everything that followed. It meant that the next generation of stars, population 2 stars, would form from gas that was ever so slightly enriched with these heavy elements. This allowed gas clouds to cool more efficiently and fragment, leading to the formation of smaller, longer-lived stars. And eventually, after generations of stellar life and death had seeded the cosmos with a rich array of elements, the stage was set for the formation of rocky planets, organic molecules, and ultimately life. So, while we have yet to directly observe a population 3 star, their ghostly imprint is everywhere. Every atom of oxygen you breathe, every particle of iron in your blood, was forged in the heart of a star that died long ago. We are quite literally the legacy of those first magnificent giants that illuminated the dark. But if those first stars were the brilliant actors on the cosmic stage, we must now turn our attention to the stage itself, the invisible scaffolding that dictated where and when the lights could turn on. This brings us to a theory so fundamental that it underpins nearly every modern understanding of cosmic evolution: the dominant influence of dark matter. We've mentioned it in passing, but it's time to truly appreciate the role of this mysterious substance. Think of it as the universe's master architect, an unseen director silently guiding the construction of everything we can see. For the first galaxies to form, they needed a gravitational anchor, a focal point to gather the diffuse gas of the early universe. Dark matter provided that anchor. To grasp why dark matter was so crucial, we need to understand a key limitation of normal matter. After the Big Bang, the universe was a searingly hot plasma, a soup of particles where protons and electrons were separated. This plasma was under immense pressure, and pressure creates a force that pushes back against gravity's relentless pull. So, when gravity tried to compress a region of this hot gas, the pressure would effectively create sound waves density oscillations that traveled through the cosmos, preventing the gas from collapsing into small, tight clumps. It was like trying to compress a spring. The harder you push, the more it pushes back. This meant that normal matter on its own was stuck in a kind of cosmic stalemate for the first several 100,000 years. Dark matter, however, played by a completely different set of rules. We believe it doesn't interact with light or electromagnetic forces at all. It is, for all intents and purposes, invisible and frictionless. Crucially, it also doesn't feel the pressure that plagued normal matter. This gave dark matter a monumental head start. While the ordinary matter was still a hot, jostling, pressurized fluid, dark matter particles could simply pass right through each other and the plasma unaffected. The only force they responded to was gravity. So, those tiny quantum fluctuations in density, dark matter began to amplify them immediately. Without any pressure to resist, slight overdensities of dark matter could start collapsing right away, quietly forming clumps in the darkness while the visible universe was still a blindingly bright, opaque fog. These clumps are what we call dark matter halos. The term halo is a bit misleading. It's not a glowing ring. Instead, imagine a vast spherical cloud of this invisible matter, one that is densest at its center and becomes more diffuse as you move outward. Each halo creates a gravitational well, a depression in the fabric of space-time. After the universe expanded and cooled enough for electrons and protons to combine into neutral atoms, an event known as recombination, the cosmic plasma cleared. The ordinary gas was finally free from the pressure of radiation and could now respond purely to gravity. And what was the strongest gravitational signal? The wells carved out by those pre-existing dark matter halos, the hydrogen and helium gas began to stream into these invisible pits, pooling at their centers. This is the moment when the potential for galaxy formation truly began. The dark matter halos provided the gravitational blueprint. The normal matter simply followed the plan, flowing into the templates that had been under construction since almost the beginning of time. But the story doesn't end there. the specific nature of dark matter itself becomes a critical variable, a key that unlocks different scenarios for how the first structures emerge. The prevailing theory, and the one that fits most observational data, is known as cold dark matter. This model proposes that dark matter particles are slow-moving and heavy. Because they are cold, they can clump together on very small scales, leading to the hierarchical bottom-up structure we discussed earlier. In a cold dark matter universe, a vast number of Earth mass-sized halos could have formed first, eventually merging into larger structures. This would have allowed for a universe teeming with tiny, early proto-galaxies. However, other possibilities exist. What if dark matter is warm, meaning the particles are lighter and faster? Warm dark matter would have a profound effect. These faster-moving particles would smooth out the smallest fluctuations, preventing the formation of those tiny halos. In a warm dark matter cosmos, the first structures to form would be much larger, skipping the small-scale building blocks entirely. This would delay the formation of the very first stars and galaxies and create a noticeably different distribution of dwarf galaxies in the universe today. Astronomers are actively using powerful telescopes to census the population of small, faint galaxies in the early universe. Finding an abundance of them strongly supports the cold dark matter model, while a surprising lack could point toward a warmer, more exotic type of dark particle. So, by studying the first galaxies, we are not just learning about stars and gas. We are conducting a fundamental test of the universe's invisible ingredients, probing the very nature of the matter that holds it all together. Yet, with this invisible dark matter scaffolding in place, what set the initial pattern for where those first galaxies would actually begin to clump? The answer lies in an echo from a much earlier time, a fossilized imprint from the universe's infancy that provided the original blueprint for the cosmic web. This brings us to a theory that deals with the very first vibrations of reality, baryonic acoustic oscillations. To understand this, we need to journey back to a period even before the Dark Ages, to a time when the entire cosmos was a searing, brilliant fireball. In the first 400,000 years after the Big Bang, the universe was not transparent. It was an opaque, dense soup of plasma. In this primordial inferno, the fundamental particles of light, called photons, were tightly entangled with the particles of normal matter, known as baryons, which are primarily protons and neutrons. Imagine this plasma as an incredibly hot, dense fluid, but this fluid was not perfectly still. Remember those tiny quantum fluctuations that seeded all structure. They also created minute variations in density within this plasma. A region that was slightly denser had stronger gravity, which tried to pull more material inward. However, there was a powerful opposing force, the immense pressure from the trapped photons. This push and pull between gravity's inward crush and radiation's outward pressure set the entire plasma into motion, creating colossal sound waves that rippled outward from every single density peak. These weren't sound waves as we hear them, but rather spherical density waves propagating through the early universe at a significant fraction of the speed of light. For nearly 400,000 years, these waves expanded outward from every overdense region. Then, a pivotal event occurred, recombination. As the universe expanded and cooled, it finally reached a temperature cool enough for electrons and protons to combine and form neutral hydrogen atoms. In an instant, the photons, which had been constantly bouncing off the free electrons, were suddenly set free. The universe became transparent. This moment of liberation is what we see today as the cosmic microwave background radiation, the afterglow of the Big Bang. But just as importantly, the sound waves traveling through the plasma were instantly frozen in place. Without the charged particles to interact with, the waves simply stopped. The baryonic matter that had been carried along by the wavefront was deposited at a fixed distance from the original center, like a shell of material. This created a universal preferred scale, a standard ruler etched into the fabric of the cosmos. the distance that sound could travel in that 400,000-year period, about 500,000 light years, became imprinted on the distribution of matter. After recombination, this matter, now neutral gas, would eventually collapse under gravity to form the first galaxies and clusters, but it would do so with this ancient pattern as its underlying template. So, what does this mean for the universe we see today? It manifests as a subtle but incredibly significant statistical tendency. When astronomers map the positions of millions of galaxies across vast volumes of space, they don't see a perfectly random distribution. Instead, they find that galaxies are slightly more likely to be separated by a specific distance, a distance that corresponds to that frozen sound wave, scaled up by the expansion of the universe to nearly 500 million light-years today. This pattern is the baryonic acoustic oscillation. It's a faint whisper of the universe's fiery birth, a cosmic echo that provides a fossilized imprint of its initial conditions. This theory is profound because it gives us the starting point. The dark matter halos formed within this pre-existing framework, and the gas that flowed into them to create stars and galaxies was already distributed with this subtle, rhythmic spacing. It's the reason the cosmic web has a characteristic scale to its filaments and voids. By measuring this preferred separation with exquisite precision, astronomers have not only confirmed our model of the early universe, but have also turned these oscillations into a powerful tool for measuring cosmic expansion itself, providing a rigid yardstick to track the history and fate of the entire cosmos. However, the brilliant dawn brought by those first stars and galaxies carried with it a profound consequence, a cosmic paradox where the very act of creation began to stifle further growth. This brings us to a critical turning point in cosmic history known as the epoch of reionization, a period where the universe underwent a fundamental environmental shift. For hundreds of millions of years after the Big Bang, the cosmos was filled with a fog of neutral hydrogen gas. This gas was transparent to certain types of light but acted like a thick curtain, absorbing the high-energy ultraviolet radiation that the first massive stars began to produce. The ignition of these stellar powerhouses initiated a monumental battle between light and shadow. The ultraviolet photons pouring from these first stars and early galaxies were incredibly energetic. As they traveled through space, they would slam into the neutral hydrogen atoms that filled the universe. When a photon hit an atom, it delivered a powerful kick, enough to blast the electron right off the proton. This process, called ionization, effectively stripped the atoms bare, turning the neutral hydrogen fog back into a hot, diffuse plasma of individual protons and electrons. Think of it as a cosmic heat wave, a wavefront of energy that swept across the universe, gradually burning away the primordial mist. This was the era of reionization, the universe's great transformation from an opaque, neutral state to the transparent, ionized condition we see today. It was not an instantaneous flash, but a gradual process, a patchwork of ionized bubbles growing around the first luminous sources, eventually overlapping until the entire cosmic volume was clear. This clearing of the fog had a dramatic and perhaps counterintuitive effect on galaxy formation. While it made the universe transparent to light, allowing photons to travel freely for the first time, it also made it much more difficult for new galaxies to form, particularly the smaller ones. Here's why. For a galaxy to form, a cloud of gas needs to collapse under its own gravity. To collapse, the gas must be able to cool down. As gas condenses, it heats up, and if that heat can't escape, the increased pressure will halt the collapse. Neutral hydrogen is very efficient at cooling. It can radiate heat away, allowing the cloud to continue condensing. But once the gas is ionized, it becomes a hot plasma. This hot, ionized gas has a much harder time cooling efficiently. It's like the difference between trying to cool down a hot stone by throwing it into a cool lake versus trying to cool it in a sauna. The environment itself had become hostile to the delicate process of collapse. This created a powerful form of cosmic feedback. the first galaxies, by simply shining their light, fundamentally altered the conditions of their surroundings. They heated the intergalactic medium, making the gas too hot and energetic to easily fall into the gravitational wells of new, smaller dark matter halos. A small halo with relatively weak gravity simply wouldn't be able to pull in the hot, high-pressure gas that was now swirling around it. This meant that the formation of smaller, dwarf galaxies could have been significantly suppressed or even delayed for hundreds of millions of years. The universe, once it began to light up, may have effectively put a lower limit on the size of galaxy that could form from the pristine gas. The era of building galaxies from tiny building blocks may have been brought to an abrupt end by the very first generation of cosmic pioneers. This theory makes the study of reionization one of the most active and exciting areas in modern cosmology. When exactly did it start, and how long did it take? Was it driven primarily by the first massive stars, by early galaxies, or by even more exotic objects like quasars? The answers to these questions are written in the faint light that has traveled from that era, and unlocking them is a primary mission for the James Webb Space Telescope. JWST is designed to look back to the time when the first galaxies were forming and observe them directly. By counting the number of small, faint galaxies at these incredible distances, astronomers can test whether there were enough of them to drive reionization. Furthermore, by studying the spectra of the most distant quasars, we can see how their light has been absorbed by patches of lingering neutral hydrogen along the way, charting the progress of the ionization fronts. Understanding reionization is not just about mapping a historical event. It is about understanding the self-regulating mechanisms of the cosmos, how the first structures shaped the entire future of galaxy formation, and ultimately the landscape in which our own Milky Way would one day emerge. Building on the idea of reionization's cosmic feedback, we must now venture to an even earlier and more fundamental scale, to the very cradles where the first sparks of starlight might have ignited. This is the theory of mini-halos, a concept that takes us to the absolute frontier of the universe's first light. If the first galaxies were the cities of the cosmic dawn, then mini-halos represent the isolated, primitive villages, the very first attempts at construction in a dark and empty world. These were not the massive dark matter halos that would later host grand galaxies. Instead, they were the smallest possible gravitational wells, with masses perhaps only a few 100,000 times that of our Sun, barely enough to gather a wisp of primordial gas. Within these minuscule halos, the physics of star formation was a delicate and precarious dance. The primary challenge was cooling. For gas to collapse and form a star, it must shed the heat generated by its own gravitational infall. In later generations of stars, this is easily accomplished by elements like carbon and oxygen, which are excellent at radiating away energy. But in the pristine environment of a mini-halo, these metals did not yet exist. The only coolant available was molecular hydrogen. You can think of hydrogen molecules as very simple, inefficient radiators compared to the complex metal-based cooling systems that would come later. A cloud of pure hydrogen and helium gas trying to cool through molecular hydrogen is like trying to chill a room with a single, small ice cube instead of a powerful air conditioner. It works, but just barely and under very specific conditions. This inefficiency had a direct consequence for the types of stars that could form. Because the gas couldn't cool down rapidly, it couldn't fragment into many small pieces. Instead, the collapse within a mini-halo was slow and monolithic, funneling a relatively large amount of gas, perhaps tens or even hundreds of solar masses, into a single massive object. This lends strong support to the theory that the very first stars born in these environments were the colossal population, three behemoths we discussed earlier. The formation process itself was fragile. The faint ultraviolet background light that began to build up as the first stars ignited could easily destroy the delicate molecular hydrogen in neighboring mini-halos. This phenomenon, known as photodissociation, would have shut down star formation before it could even begin, sterilizing these small potential sites and effectively imposing a minimum size for a halo that could form stars in an increasingly illuminated universe. This leads to a central and ongoing debate among cosmologists. Were these mini-halos efficient star factories, or were they merely stepping stones? One school of thought suggests they were the true pioneers, hosting the very first brilliant, if short-lived, stars that began the process of reionization. In this scenario, the cosmic dawn was not a single, coordinated event but a gradual brightening, with isolated points of light flickering on one by one across the vast darkness. The other perspective argues that the challenges were simply too great. The cooling was so inefficient and the gravitational pull of these small halos so weak that any star formation would have been extremely rare. Instead, mini-halos may have primarily acted as reservoirs of pristine gas, waiting to be gravitationally swallowed up by larger, more massive halos that formed slightly later. In this view, they were not the birthplaces of the first stars, but rather the raw building material that fueled the first true galaxies. The answer likely lies somewhere in between, and it is a question that the James Webb Space Telescope is uniquely equipped to address. By peering back to the very edge of observable time, astronomers hope to detect the faint signatures of these first stellar villages, to see if the universe's initial light came from a few scattered giants or from a more widespread population of smaller, fainter objects. Unraveling this mystery is key to understanding the true timeline of cosmic enlightenment. Now, to truly grasp the origin of those first galactic blueprints, we must journey back to an era that defies imagination, to the very first moments of existence. This brings us to a theory that is as profound as it is elegant, a concept that sets the stage for everything to come: cosmic inflation. We need to rewind the cosmic clock to a time so early that the universe was just a fleeting fraction of a second old. At this incalculably hot and dense starting point, the cosmos as we know it was plagued by a mystery. Observations of the cosmic microwave background show a universe that is remarkably, almost perfectly, uniform in temperature from one end to the other. But there's a puzzle. Regions of space that are now on opposite sides of the observable universe were once so far apart that not even light could have traveled between them to equalize their temperature. How then did they manage to reach the same thermal state? It's like walking into two identical rooms that have never been connected. The theory of inflation provides a stunning solution. It proposes that in the first sliver of a second after the Big Bang, the universe underwent a period of exponentially rapid expansion, inflating from a subatomic speck to something trillions of times larger in the blink of an eye. This wasn't the steady, stately expansion we see today. It was a violent, hyper-fast stretching of spacetime itself. This explosive growth solves the uniformity problem effortlessly. Before inflation, the entire observable universe was a tiny, connected region, small enough for everything to interact and smooth out any temperature differences. Inflation then took this smooth, uniform patch and stretched it to cosmic proportions, creating the vast, even-temperatured cosmos we observe. But inflation's most crucial gift to the cosmos was not uniformity. It was the introduction of imperfection. Even in that primordial, ultra-small state, the universe was subject to the jittering, unpredictable rules of quantum mechanics. At the quantum level, empty space is never truly empty. It is a seething foam of virtual particles constantly flickering in and out of existence. These fleeting quantum fluctuations create tiny, random variations in energy density. Under normal circumstances, these fluctuations are microscopic and insignificant, but inflation acted like a cosmic amplifier. As space-time expanded at an unimaginable rate, it stretched these infinitesimal quantum ripples, these tiny bumps and wiggles across astronomical distances. What were once quantum fluctuations on a scale billions of times smaller than an atom were inflated to become macroscopic variations in the density of the universe. Think of it like stretching a piece of rubber with a fine, random texture. As you pull the rubber, the tiny bumps and grooves are magnified, becoming large hills and valleys. Inflation did exactly this to the fabric of space-time. When the inflationary period ended, the energy driving it decayed into the hot soup of particles of the Big Bang fireball, but it left behind an indelible imprint. The universe was no longer perfectly smooth. It was now imprinted with those amplified quantum ripples, creating a pattern of slightly denser regions and slightly less dense regions spread throughout all of space. This pattern, this fossilized quantum noise, became the ultimate blueprint, the primordial seed catalog for all future structure. These minuscule density differences, now frozen into the distribution of matter and energy, were the only game in town. Gravity is a patient force, but it is relentless. Over the hundreds of millions of years that followed, gravity began to work on these seeds. It preferentially pulled matter toward the slightly denser regions. The overdense spots grew denser, attracting more and more gas and dark matter, while the underdense regions were slowly evacuated, becoming the vast cosmic voids we see today. The specific pattern of these initial ripples, dictated by the physics of inflation, is predicted to have a particular statistical signature, a certain distribution of large, medium, and small density variations. And when we look at the detailed map of the cosmic microwave background, and later at the large-scale distribution of galaxies, we see that exact signature. The observed cosmic web, with its filaments and clusters, matches the pattern predicted by the simplest models of inflation. This is why inflation is considered a cornerstone of modern cosmology. It elegantly solves major puzzles while simultaneously providing the mechanism for generating the grand architecture of the universe from the ghostly dance of the quantum world. Without that brief, violent burst of expansion, the cosmos might have remained a featureless, sterile sea of gas, devoid of the galaxies, stars, and planets that make our universe rich and complex. We've explored how the first stars and the process of reionization began to shape the early universe, but there is another, even more violent and disruptive force that may have played a critical role in regulating the growth of these infant galaxies. This is the theory of feedback from supermassive black holes, a concept that introduces a truly monstrous presence at the heart of cosmic evolution. Imagine a fledgling galaxy, a swirling disk of gas just beginning to light up with its first generation of stars. Deep within its chaotic center, a seed of unimaginable density is forming, a supermassive black hole. This isn't a quiet, dormant object. It is an active, ravenous engine, and its appetite can dictate the entire future of its host galaxy. These cosmic powerhouses are known as active galactic nuclei, or AN. At their core lies a supermassive black hole with a mass millions or even billions of times greater than our Sun. As vast amounts of gas and dust spiral inward, drawn by the black hole's immense gravity, this material doesn't just vanish quietly. It forms a superheated, glowing accretion disk, a maelstrom of matter moving at nearly the speed of light. Friction and magnetic fields within this disk heat the gas to temperatures of millions of degrees, causing it to emit a phenomenal amount of radiation across the entire spectrum, from X-rays to radio waves. This single object can outshine all the stars in its galaxy combined. But the most dramatic effect isn't just the light show, it's the powerful outflows that this activity generates. Some of the infalling matter, instead of crossing the event horizon, is channeled and propelled outward at incredible speeds by intense magnetic fields and radiation pressure. These are the astrophysical jets and winds, colossal beams of energy and particles that can blast clear across the galaxy and far out into intergalactic space. The energy carried by these outflows is staggering, equivalent to the simultaneous explosion of millions of supernovae. When this directed fury slams into the surrounding reservoir of cold gas, the very fuel required to form new stars, the effect is catastrophic for star formation. The incoming shockwaves heat the gas to extreme temperatures, preventing it from cooling and collapsing. In even more extreme cases, the winds can physically push the gas right out of the galaxy, stripping it of its star making potential in an event known as quenching. This process is a powerful form of negative feedback, a cosmic self-regulation mechanism. It answers a fundamental question: why don't galaxies just keep growing forever? Why is there an observed relationship between the mass of a galaxy's central bulge and the mass of its supermassive black hole? The feedback theory provides the answer. In the early universe, as a galaxy grew, so too did its central black hole. But there was a point where the black hole became so energetic that its outbursts began to disrupt the gas supply that was feeding both its own growth and the formation of new stars. It effectively put a brake on the entire system. A galaxy could, in a sense, strangle its own future by nurturing too powerful a monster in its core. This intimate connection, this cosmic feedback loop, is why astronomers today see such a tight correlation between black hole mass and galaxy properties. The history of each is irrevocably intertwined. The idea that some of the very first galaxies could have hosted such powerful agents is a testament to the rapid and dynamic nature of the early cosmos. The seeds for these supermassive black holes are a subject of intense debate. Perhaps they formed from the collapse of the first supermassive population 3 stars, or maybe from the direct collapse of massive gas clouds. Regardless of their origin, their presence would have introduced a new and decisive factor in the galaxy formation game. While some galaxies grew steadily, others might have had their growth abruptly truncated by the ferocious activity of their central black holes, creating a diverse population of galaxies from the very beginning. This theory transforms our view of galaxy evolution from a simple story of gravitational accumulation to a more complex narrative of construction and destruction, where the most luminous and destructive objects in the universe also serve as its ultimate architects, shaping the cosmic landscape through their explosive feedback. Having explored the colossal forces of black holes and the quantum seeds of inflation, we now turn to a far more subtle, yet potentially equally fundamental, player in the cosmic drama: the role of magnetic fields. We often think of the early universe in terms of gravity and radiation, but magnetism adds a third, invisible dimension to the forces at work. Imagine the primordial gas, a vast sea of hydrogen and helium, beginning its slow dance under gravity's pull. Now picture this entire process happening within an invisible web of magnetic field lines, like delicate threads woven through the fabric of space itself. Could these fields have guided the collapse of the first gas clouds, leaving an imprint on the very first stars? The question of where cosmic magnetic fields come from is a deep mystery. Today, we see magnetic fields everywhere, threading through planets, stars, and entire galaxies. But were they present from the very beginning, or were they born later? This is the theory of primordial magnetic fields. The idea is that incredibly weak magnetic fields could have been generated during the universe's violent infancy, perhaps during the phase transitions of the early cosmos, or even during inflation itself. These fields would have been unimaginably faint, billions of times weaker than the magnetic field of the Earth. In the grand scheme of things, gravity would have been the dominant force, overwhelming such a weak magnetic influence. However, on the small scales relevant to star formation, even a feeble field could have played a crucial role. The key lies in how magnetic fields interact with ionized gas or plasma. A magnetic field exerts a force on charged particles, causing them to spiral along the field lines. This has two major effects. First, it can provide a form of pressure that supports a gas cloud against its own gravity, slightly slowing down the collapse. Second, and more importantly, it can resist the twisting and bending motions of the gas. As a cloud collapses and begins to rotate, magnetic fields get dragged along and wound up. This magnetic tension acts like a spring, fighting against the gas's motion and influencing how the cloud fragments. In a pristine cloud without metals, this magnetic friction could have been a critical factor in determining whether a cloud broke apart into multiple smaller stars or funneled its material into a single, monstrous population 3-star. But the story doesn't end with these weak primordial seeds. Once the first structures began to form, a powerful engine kicked in to amplify these fields dramatically, the galactic dynamo. Think of a dynamo as a cosmic generator. As a young galaxy rotates, its turbulent motions and differential rotation, where the inner parts spin faster than the outer parts, can stretch, twist, and fold the weak primordial magnetic field lines. This process, similar to how a dynamo on a bicycle amplifies a small magnetic field to power a light, can exponentially strengthen the magnetic field over millions of years. What began as a feeble, universe-wide whisper could be transformed into the strong, organized magnetic fields we observe in galaxies today. This amplification would have further influenced the galaxy's evolution, helping to launch outflows, confining cosmic rays, and regulating the birth of subsequent generations of stars. The challenge, of course, is evidence. Detecting the faint imprint of a primordial magnetic field is one of the most difficult tasks in cosmology. Astronomers search for subtle effects on the cosmic microwave background or look for specific signatures in the polarization of light from the most distant quasars. If such a field were detected, it would be a monumental discovery. It would provide a direct window into physics at energy scales far beyond what any particle accelerator on Earth can reach, offering clues about the fundamental symmetries of the universe in its first moments. The presence of a primordial magnetic field would mean that the cosmic playing field was never entirely level. From the very start, an invisible lattice of force was in place, silently guiding the flow of gas and perhaps even setting the stage for the magnetic tapestry that now connects the cosmos. Yet, even as we map out the grand construction plans governed by gravity, dark matter, and black holes, astronomers have uncovered a pattern in the present-day universe that challenges our simplest assumptions about how galaxies mature. This is the puzzling observation known as galaxy downsizing. If the hierarchical model is correct and large galaxies are built from the mergers of smaller ones, you might logically expect the smallest galaxies to form first, with the giants assembling later. But the cosmos, it seems, enjoys a good paradox. What we actually observe is the complete opposite. The most massive galaxies finished their star-forming business early in cosmic history, while their smaller cousins have continued to create stars at a more leisurely pace right up to the present day. Think of it as a cosmic retirement party where the wealthiest guests arrived first, built their fortunes in a frantic rush, and then left the party early, while the smaller guests showed up later and are still mingling and slowly accumulating. The evidence for this is striking. When we look at the most massive elliptical galaxies in the nearby universe, we find that their stars are uniformly old. The vast majority of them were formed in an intense burst of activity that peaked around 10 billion years ago, and since then, these galaxies have been largely dormant, what astronomers call red and dead. They are cosmic relics. In contrast, smaller dwarf galaxies and even many spiral galaxies like our own Milky Way have continued to form new stars at a modest rate throughout cosmic time. This pattern of the biggest galaxies aging first is what we call downsizing, and it turns the intuitive bottom-up growth story on its head. So, what cosmic mechanism could cause the largest structures to rapidly exhaust their fuel and shut down, while smaller systems keep chugging along? One of the leading explanations brings us back to the awesome power of active galactic nuclei, or AN. The theory suggests that feedback from supermassive black holes is not just a regulatory force, it is a selective one, and its effects are most devastating in the most massive galaxies. Here's why. The energy output from an AGN is titanic, but to effectively quench star formation across an entire galaxy, that energy must be efficiently transferred to the vast reservoirs of cold gas. In a truly massive galaxy with a correspondingly massive dark matter halo, the gravitational well is incredibly deep. Gas falling into this well gains immense speed, and when it is eventually heated by an AGN outburst, it can achieve the velocity needed to escape the galaxy's gravitational pull entirely in a process known as ejective feedback. The sheer scale of the system works against it, allowing the central black hole to violently expel its future fuel supply into intergalactic space. For a smaller galaxy with a shallower gravitational well, the same AGN outburst might simply heat the gas, temporarily pausing star formation until the gas can cool and fall back in. But for the giants, the feedback is often a final, terminal event. Another compelling angle focuses on the unique environment of the early universe itself. In the first few billion years after the Big Bang, the universe was much smaller and denser. Gas was everywhere, and it was pristine and cold, perfect for rapid star formation. The largest dark matter halos, with their stronger gravity, were exceptionally efficient at funneling this abundant cosmic fuel into their cores. This led to an era of explosive growth for the progenitors of today's massive galaxies, a period often called galactic adolescence. They gorged themselves on the readily available gas, converting it into stars at a ferocious rate that is almost unimaginable in the present-day universe. Our own Milky Way might form 1 or 2 new stars per year on average. A massive starburst galaxy in the early universe could form hundreds or even thousands of stars in that same time. This theory proposes that the biggest galaxies simply finished their main course of star formation first because they had access to an all-you-can-eat buffet that later generations of galaxies could only dream of. They consumed the richest resources in their youth, leaving behind a more diffuse and heated intergalactic medium for the smaller, slower-forming galaxies to work with. This combination of factors, AGN feedback operating with brutal efficiency in deep gravitational wells, and a primordial environment of abundant gas, may provide the key to understanding downsizing. It paints a picture of a universe where the rules of growth change over time. The initial phase is a land rush where the largest structures claim the best territory and develop rapidly. But this very success contains the seeds of its own demise, as the central black holes they nurture eventually rise up to cut off their fuel supply. Meanwhile, smaller galaxies, forming in less dense environments or later in cosmic history, avoid this dramatic fate. Their slower, more sustained evolution allows them to continue forming stars long after their colossal neighbors have faded into quiet retirement. This nuanced view helps reconcile the bottom-up assembly of dark matter with the top-down quenching of star formation, showing us that the history of galaxies is not a simple story of growth, but a complex ballet of creation and destruction, feast and famine. But if the first galaxies built themselves from the ground up and were then shaped by the disruptive feedback from black holes, we are still left with a practical puzzle. How exactly did they acquire the vast amounts of fuel needed to power such incredible bursts of star formation so early in the universe's history? This brings us to a theory that offers a surprisingly elegant and efficient delivery system for cosmic gas, a method that bypasses the traditional bottlenecks of galaxy growth. This is the cold flow accretion model, and it paints a picture of the early universe crisscrossed by icy rivers of primordial fuel, flowing directly into the hearts of hungry young galaxies. To appreciate the cold flow model, we first need to understand the standard, more gradual way that galaxies were thought to gather gas. In the later, more evolved universe, when a galaxy attracts gas from its surroundings, that gas has a rough journey. As it falls into the galaxy's dark matter halo, it collides with other gas particles. These collisions generate immense heat, causing the incoming gas to shock heat to temperatures of millions of degrees. Before this hot gas can form any stars, it must first cool down, a process that can take hundreds of millions of years. It's a slow, inefficient trickle-charge system. But when we look at the earliest galaxies with telescopes like JWST, we see evidence of immense star formation rates happening at a breakneck pace, far too quickly for this slow hot mode accretion to explain. The cold flow model provides a stunning alternative. It suggests that in the dense, youthful cosmos, gas didn't need to heat up at all. Instead, it could travel from the vast reservoirs of the cosmic web directly into the centers of galaxies along pre-existing highways. These highways are the dense filaments of dark matter that form the skeleton of the cosmic web. Imagine these filaments not as abstract lines, but as vast gravitational aqueducts. The pristine hydrogen and helium gas drawn in by the filament's gravity would naturally flow along these narrow channels. Because the flow is concentrated and directed, the gas particles don't crash into each other chaotically. Instead, they stream together in a coherent, dense current. Without those violent collisions, the gas never shock heats. It remains cold. This creates a direct pipeline from the intergalactic medium to the galaxy's core. Picture a mountain river fed by melting snow, flowing swiftly and cold into a valley lake. The cold flow model proposes rivers of cosmic gas, chilled to just a few tens of thousands of degrees above absolute zero, streaming along the dark matter filaments. When two or more of these filaments intersect, their cold gas flows converge at the nexus point, the location of a nascent galaxy. This delivers a massive, continuous supply of cold, star-forming fuel directly to the engine room, bypassing the hot halo entirely. It's the difference between trying to fill a swimming pool with a misting hose versus opening a floodgate. This rapid, cold mode accretion could easily explain the intense starbursts we see in the earliest galaxies, allowing them to build up their stellar mass at an astonishing rate. The cold flow model is particularly powerful for explaining the growth of galaxies in the early universe, when the cosmic web was denser and these cold streams were more prominent. It suggests that the most prolific star-forming galaxies were those situated at the busiest intersections of the cosmic web, where multiple cold gas rivers merged, fueling a veritable frenzy of star birth. This theory elegantly connects the large-scale structure of the universe, dictated by dark matter, with the small-scale process of star formation within individual galaxies. It shows us that galaxies are not isolated islands in space. They are deeply connected to the cosmic currents that flow through the universe, their growth and brilliance dictated by the invisible rivers that feed them. This relentless assembly process, governed by the hierarchical model, sets the stage for one of the most dramatic and transformative events in a galaxy's life, a merger. While the cold flows of gas provide the fuel, it is the collisions between galaxies themselves that act as the great architects of cosmic structure, reshaping and rebuilding in violent, spectacular fashion. The theory of galaxy mergers and transformations reveals a universe in constant, dynamic flux, where the serene spirals we see today are the survivors of a long and turbulent history of cosmic crashes. To understand the sheer power of a merger, consider our own Milky Way. It appears as a stable, majestic pinwheel of stars, but this is merely a snapshot in time. We are surrounded by evidence of our cannibalistic past. The galactic halo, a vast spherical cloud of ancient stars enveloping the main disk, is thought to be the fossilized remains of smaller galaxies that our Milky Way consumed billions of years ago. And we are not done. The Milky Way is currently in the process of tearing apart and absorbing several dwarf galaxies, like the Sagittarius dwarf spheroidal. This ongoing feast is a minor merger, a gentle nibble compared to the colossal collisions that defined the early universe. In the dense, youthful cosmos, such encounters were not the exception, they were the rule. Mergers are broadly categorized by the mass ratio of the participants. A minor merger occurs when a large galaxy consumes a much smaller satellite, While less destructive, these events are far from insignificant. As the smaller galaxy is pulled in by gravity, its stars are stripped away, forming vast, diffuse streams and shells around the larger galaxy, building up its stellar halo. The gravitational turbulence can also puff up the main galaxy's disk, contributing to the formation of a thicker, more disordered stellar component. It's a gradual process of cosmic accretion, like a large city annexing its surrounding towns. But it is the major merger that truly rewrites a galaxy's destiny. This is a head-on collision between two galaxies of roughly comparable size. Imagine two magnificent spiral galaxies, each with hundreds of billions of stars, on a slow-motion collision course over hundreds of millions of years. Despite the vast distances between stars making direct stellar impacts incredibly rare, it is the immense gravitational forces that wreak havoc. As the galaxies first approach, their mutual gravity stretches them, pulling out long, luminous tendrils of gas and stars known as tidal tails. These are the cosmic fingerprints of a violent embrace. During the merger, the neat, orderly orbits of stars within the original disks are completely scrambled. The gravitational chaos randomizes their paths, transforming the two structured spirals into a single, blob-like ellipsoid of stars, an elliptical galaxy. This is why we see so many elliptical galaxies in the dense environments of galaxy clusters. They are the products of a violent past, the survivors of repeated mergers that have erased all traces of their disky origins. But the transformation is not just about the stars. The real fireworks come from the gas. While stars mostly pass by each other, the colossal clouds of gas within the galaxies slam directly into one another. This sudden, extreme compression triggers a ferocious burst of star formation, known as a starburst. In a starburst galaxy, the rate of star formation can be hundreds of times greater than in a normal galaxy like the Milky Way, lighting up the universe with the birth of millions of new stars in a relatively short cosmic time. Perhaps the most profound consequence of a major merger is what it does to the central supermassive black holes lurking in the heart of each galaxy. As the gas is driven violently inward by the gravitational turmoil, vast amounts of it are funneled directly toward these black holes. This delivers an unprecedented feast, igniting them as brilliant active galactic nuclei. This intimate link between mergers and AGN activity is a cornerstone of modern astrophysics, explaining why the most luminous quasars, the most powerful engines in the universe, are often found in galaxies showing clear signs of a recent collision. The merger provides the mechanism to transport fuel from the outer regions of a galaxy all the way to its very center, awakening the monster within. Eventually, the two black holes themselves will spiral toward each other, destined to merge in a cataclysm that will ripple the fabric of space-time with gravitational waves. So, the theory of mergers shows us that a galaxy's morphology, whether it is a spiral, an elliptical, or something in between, is not set in stone from birth. It is a testament to its history. A quiet life of steady gas accretion may preserve a delicate spiral disk. A major merger can completely erase that disk, leaving behind a featureless elliptical. This dynamic view transforms our understanding of galaxies from static islands to evolving organisms, whose shapes and fates are forged in the fiery collisions of their youth. While the story of galaxy formation often focuses on the brilliant spirals and massive ellipticals, the cosmos holds a deeper secret, a class of objects so ghostly they challenge our most fundamental ideas about what a galaxy even is. These are the ultra-diffuse galaxies, or UDG, and their existence presents a fascinating puzzle. Imagine a galaxy that spans the same vast diameter as our own Milky Way, a majestic wheel of stars tens of thousands of light-years across. Now imagine that this enormous structure contains not hundreds of billions of stars, but only a few billion or even less. The result is a celestial phantom, a galaxy with such a low density of stars that it is almost transparent, a wispy cobweb of ancient suns drifting in the darkness. For a long time, these ghostly giants remained hidden in plain sight, their faint light lost in the glare of brighter neighbors or drowned out by the foreground stars of our own galaxy. It took advances in telescope technology and meticulous surveys to finally pull them out of the shadows. Their discovery sent a ripple through the astronomy community because they simply don't fit the standard mold. According to our standard models, a galaxy's size and its stellar mass are generally correlated. A large galaxy has a deep gravitational well that pulls in a lot of gas, leading to the formation of a vast number of stars. Ultra-diffuse galaxies break this rule spectacularly. They have the size of a giant but the stellar content of a dwarf, like a person with the skeleton of a basketball player but the muscle mass of a child. So, how did these cosmic paradoxes come to be? Theorists have proposed several compelling pathways for their origins, each pointing to a different, dramatic chapter in cosmic history. One leading theory suggests that UDGs are essentially failed galaxies. In this scenario, these galaxies began their lives like any other, forming within a perfectly respectable dark matter halo with enough mass to potentially become a galaxy like the Milky Way. They started to accumulate their primordial gas, and the first generation of stars may have even begun to ignite. But then, something catastrophic happened that abruptly halted their growth. A prime suspect is the epoch of reionization. As the first brilliant stars and galaxies flooded the universe with ultraviolet radiation, this intense light could have heated the gas within the protogalactic halos of UDGs to such a degree that it became too hot to continue collapsing. For a galaxy with a slightly weaker gravitational pull, this external heating might have been enough to permanently starve it of future star-forming fuel. The galaxy was left stranded, a vast dark matter framework with only a tiny population of stars that formed in that brief window before the cosmic lights came on. It had the potential for greatness, but its development was stunted at an early age, freezing it in a primordial state. Another intriguing possibility is that UDGs are not failed galaxies, but rather galaxies that have been stripped and battered by their environment. This theory places them in the dense, violent neighborhoods of galaxy clusters. Imagine an ordinary dwarf galaxy, rich with gas, that ventures too close to the gravitational heart of a massive cluster. As it falls in, it experiences extreme tidal forces, the same kind of gravitational pull that creates tides on Earth, but on a cosmic scale. These forces can slowly and methodically rip the galaxy's gas away, leaving behind only the stars which are more tightly bound by gravity. At the same time, the galaxy rams into the incredibly hot plasma that fills the space between galaxies in a cluster, a process called ram pressure stripping. This is like driving a car through a heavy downpour. The interstellar gas is simply swept away. The combination of these two environmental processes could puff the galaxy up, expanding its stellar distribution while simultaneously robbing it of the material needed to make new stars. The result is a large, diffuse, and quiescent galaxy, a ghost of its former self. There is even a more exotic third idea, that the dark matter halos of UDGs are somehow unique. Perhaps their dark matter is distributed in a much more spread out, fluffy configuration than in normal galaxies. This would create a shallower gravitational well, resulting in stars that orbit at slower speeds and are spread over a larger volume. This internal property, rather than an external event, could be the root cause of their diffuse nature. The existence of ultra-diffuse galaxies forces astronomers to broaden the narrative of galactic evolution. It shows us that the universe has more than one way to build a galaxy, and that not all evolutionary paths lead to brilliance. Some lead to quiet, ghostly giants, drifting silently through space as ancient relics of the universe's tumultuous early years, reminding us that for every grand spiral, there may be a dozen faint phantoms hiding in the dark. But if the colossal mergers of the early universe were engines of destruction, tearing apart majestic spirals to build featureless ellipticals, they also held within them a remarkable creative potential. This brings us to a theory that reveals a beautiful paradox. From the chaos of cosmic collisions, entirely new galactic worlds can be born. This is the theory of tidal dwarf galaxy formation, a process that sidesteps the conventional rules of dark matter and offers a unique pathway for creating families of stars. For all our discussion so far, the story of galaxy formation has been inextricably linked to the invisible scaffolding of dark matter. Whether through the monolithic collapse of a massive halo or the hierarchical merging of smaller ones, dark matter provided the gravitational anchor that gathered the gas necessary for star birth. Tidal dwarf galaxies, however, play by a completely different set of rules. They are not children of dark matter, but orphans of galactic violence. They form from the very debris ejected during a catastrophic encounter between two larger, gas-rich galaxies. To visualize this, picture two spiral galaxies, similar to our own Milky Way and the Andromeda Galaxy, beginning a slow, gravitational dance that will end in a merger. As they swing past each other, their mutual gravity acts like a colossal tidal force, much like the moon's pull on Earth's oceans, but on an unimaginable scale. This force is so powerful that it can wrench vast streams of gas, dust, and even some stars right out of the galactic disks. These ejected structures are the magnificent tidal tails we often see arcing away from interacting galaxies, luminous rivers of material flowing into intergalactic space. In most cases, this material will eventually fall back into the merging system or simply dissipate. But under the right conditions, something extraordinary can happen. Within these long, flowing streams of gas, pockets of material can become dense enough for their own self-gravity to take over. Imagine a long, twisting necklace where, in a few places, the beads clump together into a heavy knot. As these knots of gas collapse, they can ignite bursts of star formation. If the knot is sufficiently massive and stable, the entire clump can continue to collapse, organizing itself into a gravitationally bound object, a brand new, albeit small, galaxy. This is a tidal dwarf galaxy. What makes them so unique is their composition. Because they are formed from the outer disks and gaseous arms of their parent galaxies, they are made almost entirely of regular baryonic matter, the gas and stars that were torn away. They contain little to no dark matter from the original halos, which remains more centrally concentrated. This makes tidal dwarf galaxies living proof that galaxies can, in fact, form without a dark matter skeleton. This has profound implications for our understanding of what a galaxy truly is. It also gives them a distinct chemical signature. The material they are made from has already been processed through at least one generation of stars in their parent galaxies. This means tidal dwarfs are born with a higher metallicity, a richer abundance of elements heavier than hydrogen and helium, compared to primordial dwarf galaxies that formed from pristine gas. They are not pristine relics of the early universe, but rather second-generation objects built from the recycled remains of earlier stellar generations. While we observe tidal dwarf galaxies forming today in nearby galaxy collisions, this process was almost certainly far more common in the chaotic, crowded environment of the early universe. When galaxies were closer together and gas was the dominant component of galactic disks, every major interaction would have flung enormous quantities of star-forming material into the voids. The cosmos could have been teeming with these dark matter-poor islands, each a testament to the creative destruction that shaped the galactic landscape. Their existence reminds us that the universe is not just a story of construction from scratch, but also one of continuous recycling, where the death of one galactic structure can give birth to something entirely new and unexpected. While we often focus on the galaxies themselves as the primary actors in the cosmic story, their evolution is profoundly shaped by the vast, invisible ocean in which they are immersed. This brings us to the critical role of the intergalactic medium, or IME, the space between galaxies that is far from empty. Think of it as the cosmic ecosystem, a diffuse but all-encompassing environment whose properties dictate the rules of growth and survival for every galaxy within it. The temperature, density, and chemical makeup of this intergalactic sea are not passive background settings. They are active, dynamic forces that either enable or stifle a galaxy's development. The most fundamental way the IGM exerts its influence is through its temperature. During the epoch of reionization, as we discussed, the ultraviolet radiation from the first stars and galaxies heated the neutral hydrogen gas, ionizing it and transforming the IGM from a cool, neutral fog into a hot, ionized plasma. This shift in state had a dramatic regulatory effect. For a small, nascent dark matter halo with relatively weak gravity, pulling in fresh gas from the surrounding environment is a delicate task. If that external gas is hot and ionized, it becomes incredibly difficult to capture. The particles are too energetic, moving too quickly to be easily grabbed by the halo's shallow gravitational well. It's like trying to fill a cup from a river during a gentle rain versus trying to fill it from a high-pressure fire hose. In the latter case, the force of the water simply blows the cup away. A hot IGM therefore acts as a form of cosmic climate control, effectively suppressing the formation of small galaxies by making the fundamental fuel for star formation inaccessible to them. This environmental pressure naturally favors the growth of larger galaxies residing in deeper gravitational wells, which have the strength to overcome the gas's high pressure and continue accreting material. But the IGM is not merely a barrier, it is also the ultimate reservoir. The overwhelming majority of the universe's normal matter, the hydrogen and helium forged in the Big Bang, does not reside in galaxies. It is out there in the intergalactic void, woven into the filaments of the cosmic web. This is the raw material from which all galaxies must draw to build their stars. The concept of cold flow accretion, which we explored earlier, is entirely dependent on the IGM being structured and cool enough in these filaments to allow dense streams of gas to flow directly into galactic centers. So the IGM plays a dual role. It is the source of life-giving fuel, but it can also be a hostile environment that determines which galaxies get to drink from that cosmic well. Over billions of years, the very composition of this intergalactic reservoir changed in a process known as chemical enrichment. In the earliest universe, the IGM was pristine, containing only hydrogen, helium, and a trace of lithium. But then came the first generations of massive stars, living short, violent lives and ending in spectacular supernova explosions. These stellar deaths did more than just light up the cosmos. They became the universe's first recycling plants. The supernova blasted newly forged heavy elements carbon, oxygen, silicon, iron far out into space, polluting the pristine gas of the IGM with these metallic seeds. This enrichment was a gradual process, like adding minerals to a vast ocean, and it fundamentally altered the physics of gas cooling forever. This is a pivotal point. Heavy elements are incredibly efficient at radiating away heat. A cloud of gas enriched with even a tiny amount of metals can cool down much faster than a cloud of pure hydrogen and helium. As the IGM became progressively enriched over cosmic time, the gas within it gained a powerful new ability to shed heat. This meant that when this enriched gas eventually fell into a galaxy, it could collapse and fragment into stars much more efficiently than the primordial gas could. The enrichment of the IGM, therefore, didn't just change its chemical identity, it changed its functional role in galaxy formation. It transitioned from a simple reservoir of fuel to a pre-processed material that could accelerate the star formation process in the galaxies it fed. The intergalactic medium, once a silent backdrop, reveals itself as an active participant in the cosmic cycle, its history written in the elements that now flow between the islands of stars, governing the pace of galactic growth and the very chemistry of new worlds. But this intricate picture of cosmic evolution, built upon galaxy surveys and the cosmic web, rests on a crucial and often overlooked assumption that the galaxies we can see are faithful traces of the unseen mass that dominates the universe. This brings us to a subtle but profoundly important theory that acts as a necessary correction to our cosmic maps, the theory of galaxy biasing. It's the idea that the glittering cities of stars we observe with our telescopes are not a perfect one-to-one representation of the underlying dark matter landscape. Instead, galaxies exhibit a preference, a bias, for where they form and survive, and understanding this preference is the key to unlocking the true distribution of all matter, both seen and unseen. To grasp why biasing is so critical, imagine you're an ecologist trying to map an entire forest ecosystem, but you can only study the owls. You might notice that owls tend to live in areas with tall, mature trees. If you then used the locations of owl nests to map the entire forest, you would get a very distorted picture. You'd correctly identify the regions with the tallest trees, but you'd completely miss the meadows, the streams, the sapling groves. All the areas that are vital parts of the ecosystem but are simply not preferred owl habitats. Galaxies are the owls of the cosmos. They are a specific type of structure that forms only under certain conditions within the vast dark matter forest. They are not randomly scattered. They light up in places that meet their specific requirements for birth and survival. This bias manifests in several ways, primarily linked to a galaxy's mass and its environment. The most massive, luminous galaxies we see today are strongly biased tracers. They exhibit a powerful preference for the densest knots in the cosmic web, the rich clusters of galaxies and the intersections of dark matter filaments. There's a clear reason for this. Only the deepest gravitational wells created by the most massive dark matter halos were able to gather and retain the enormous amounts of gas needed to build a giant galaxy. A small, weak halo in an empty cosmic void simply couldn't muster the gravitational pull to become the home of a brilliant elliptical or a grand spiral. So, when we plot the positions of the brightest galaxies, we are essentially drawing a map of the highest peaks in the dark matter topography. Conversely, small, faint, dwarf galaxies show a much weaker bias or even an anti-bias. They are the cosmic equivalent of hardy plants that can grow in a wider variety of soils. While some dwarfs are satellites of large galaxies, many others can form in lower density environments, in the smaller halos that fill the filaments and even the voids of the cosmic web. They are far more numerous than their giant cousins, but they are also much harder to see across vast cosmic distances. If our telescopes are only sensitive enough to detect the brightest, most biased galaxies, our map of the universe will look overly clustered, highlighting the big cities but missing the countless small towns and isolated villages that make up the majority of the galactic population. This sampling bias can severely skew our measurements of fundamental cosmic properties, like the overall density of matter. The concept of galaxy biasing doesn't stop with location, it also involves time. The strength of this bias evolves over the lifetime of the universe. In the early cosmos, the first galaxies to form had to do so within the first and most overdense regions, the absolute peaks of the initial density field. These pioneering galaxies were, by necessity, extremely highly biased objects. As the universe expanded and evolved, gravity pulled more and more matter into larger structures, allowing galaxies to form in regions that were originally of average density. The bias diluted over time. Today, galaxy formation can occur in a much wider range of environments than it could 13 billion years ago. This evolving bias is a key ingredient that cosmologists must build into their models to accurately compare the galaxy distribution we see in the young universe with the one we see today. Without this correction, our interpretation of how cosmic structure grows would be fundamentally flawed. By carefully accounting for how different galaxies trace the mass, astronomers can use these luminous beacons not just as isolated wonders, but as precise tools to measure the invisible architecture of the cosmos itself. As we've seen, the early universe was a battlefield of constructive and destructive forces, where gravity built galaxies up while radiation and black hole winds tore them down. But there is another, more subtle player in this cosmic drama, an invisible army of particles that may have exerted a powerful influence on the growth of the first galaxies. This is the theory of cosmic ray feedback, a process where the universe's most energetic particles become agents of galactic regulation. Beyond the brilliant light of stars and the ferocious jets of black holes, this form of feedback operates in the shadows, using pure kinetic energy to shape galactic evolution. To understand cosmic rays, we need to step into the heart of cosmic violence. These are not rays of light, but rather atomic nuclei, mostly protons, that have been accelerated to nearly the speed of light. They are the ultimate cosmic bullets. Their primary sources are the most energetic events in the universe, the shock waves from supernova explosions and the powerful jets erupting from active galactic nuclei. In a supernova remnant, the expanding blast wave acts like a natural particle accelerator, a cosmic version of the Large Hadron Collider, but on an unimaginably grander scale. As these high-energy particles are generated, they don't just travel in a straight line and vanish. Instead, they become trapped by the galaxy's magnetic field, bouncing back and forth along the field lines like pinballs. This creates a vast, diffuse fog of energetic particles that fills the entire interstellar medium of a galaxy, a pervasive pressure that is felt everywhere. This leads to a crucial physical effect: cosmic ray pressure. Just like hot gas exerts pressure, this sea of relativistic particles creates its own distinct form of energy density. And because cosmic rays can travel much more easily through a galaxy than hot gas can, they're not as prone to losing energy through radiation. Their pressure can build up and propagate over large distances. Theorists propose that this buildup can have a dramatic consequence. It can help drive galactic winds. Imagine a galaxy's disk as a pressurized container. The combined energy from supernova and stellar radiation heats the gas, while cosmic rays provide an additional, persistent push. This combination can become powerful enough to overcome the galaxy's gravity, launching a fountain of gas that flows out from the disk and into the galactic halo. In some cases, this wind can be so powerful that it escapes the galaxy entirely, carrying precious star-forming fuel out into the intergalactic void. In the context of the first galaxies, this form of feedback could have been exceptionally potent. The earliest generations of stars were predominantly massive, short-lived population 3 behemoths. Their deaths in supernova explosions would have been incredibly frequent and energetic, generating an intense and continuous flux of cosmic rays. Unlike in a modern galaxy, where the interstellar medium is already enriched with elements and structured by previous generations of stars, the environment of a primordial galaxy was much simpler. There were fewer obstacles to slow down these high-energy particles, allowing the cosmic ray pressure to build up more efficiently. This means that the very first starbursts might have been self-limiting, not just by ultraviolet radiation heating the gas, but also by cosmic rays helping to physically blow the gas away. It's an elegant feedback loop. The birth of massive stars leads to their explosive deaths, which generates cosmic rays, which in turn shuts down the conditions needed for more stars to form. This process would have provided a crucial brake on the frantic pace of star formation, preventing these infant galaxies from burning through their entire fuel supply in a single, brief burst and potentially allowing for a more extended and regulated period of growth. The role of cosmic rays adds a fascinating layer of complexity to our models of galaxy evolution. It suggests that the interstellar medium is not a passive pool of gas, but a dynamic ecosystem where different forms of energy, thermal, radiative, and non-thermal from cosmic rays are in a constant struggle with gravity. By including cosmic rays in their sophisticated computer simulations, astrophysicists are finding that they can better explain the observed properties of galaxy winds and the efficiency of star formation. This theory transforms our view of supernova remnants from mere aftermaths of stellar death into active, ongoing engines that help govern the life cycle of their host galaxies, demonstrating once again that the universe operates through an intricate interplay of forces seen and unseen. While mergers and cosmic collisions paint a picture of galaxies built through external violence, there is an equally compelling theory that reveals a powerful process of internal transformation, a way for a galaxy to reshape itself from the inside out. This is the theory of proto-galactic clumps and disk instabilities, a concept that envisions a galaxy not as a serene, orderly structure, but as a turbulent, chaotic sea of star-forming fury. To understand this, we need to shift our perspective from the vast scale of the cosmic web to the intricate dynamics occurring within a single, massive, gas-rich galaxy in the early universe. Imagine one of these primordial galaxies, observed by the James Webb Space Telescope at a time when the cosmos was young. It wouldn't look like the neat, symmetrical spiral of the Milky Way. Instead, it would appear as a messy, irregular blob blazing with light. This galaxy is a colossal disk, but it's not stable. It's so incredibly rich in cold gas, the raw material for stars, that it has become gravitationally unstable. The disk is so massive and rotates in such a way that its own self-gravity overwhelms the forces, like centrifugal force and gas pressure, that would normally keep it smooth. It's like a spinning pond of water that is simply too deep. Its surface can no longer remain calm and begins to break up into a series of large, choppy waves. In this unstable environment, gravity seizes the opportunity. The entire disk begins to fragment, collapsing in on itself, not into a million tiny stars at once, but into a handful of colossal, giant clumps. Each of these clumps is not a mere star cluster. It is a monstrous, self-gravitating island of gas and young stars, each containing the mass of millions or even billions of suns. They are the building blocks of the galaxy, but they were born within the galaxy itself. These are the proto-galactic clumps, and they light up the disk like a string of brilliant pearls, each one a furious stellar nursery producing new stars at a staggering rate. The galaxy becomes a chaotic ecosystem where these giant clumps orbit within the disk, shining with an intense blue light that betrays their youth and ferocious energy. But these clumps are not destined to remain in the outer reaches of the galaxy. They embark on a grand, inward journey, and the mechanism that drives them is a subtle but relentless force known as dynamical friction. As a massive clump orbits through the sea of stars, gas, and dark matter that makes up the galactic disk, its immense gravity gravitationally tugs on the surrounding material. Think of it as a very heavy object moving through a dense crowd. It leaves a wake behind it, a slight overdensity of people it has interacted with. This gravitational wake exerts a drag force on the clump itself, slowly but surely sapping its orbital energy. The effect is that the clump's orbit begins to decay. It spirals inward over a timescale of a few 100 million years on an inevitable course toward the galactic center. This inward migration is the key to the entire process. As these giant, star-forming clumps drift toward the center, they begin to merge with one another. One by one, they deliver their immense mass both in stars and in gas to the heart of the galaxy. Through this steady accretion of clumps, the central region of the galaxy grows denser and more prominent. What began as a disordered disk gradually develops a bright, central concentration of stars, a galactic bulge. This clump accretion theory offers a powerful alternative to the idea that all bulges are formed through violent mergers with other galaxies. It suggests that a galaxy can grow its own central bulge peacefully, through a process of self-consumption, by digesting the largest structures it spawned within its own disk. This theory is particularly compelling for explaining the rapid assembly of massive galaxies observed in the early universe by JWST. many of these ancient galaxies show signs of being clumpy and disordered, exactly as the model predicts. It provides a way for a galaxy to build a dense central component quickly and efficiently without needing to wait for a rare major merger. The entire process is a beautiful demonstration of a self-regulating cycle. The galaxy's immense gas supply causes instability and fragmentation. The resulting clumps then migrate inward to build the bulge, and the growing bulge's gravity can, in turn, help stabilize the remaining disk, eventually bringing the era of chaotic clump formation to an end. It reveals a galaxy not as a static sculpture, but as a dynamic organism, capable of profound internal change that dictates its final shape and destiny. This search for the first quasars inevitably leads us to one of the most profound mysteries in all of cosmology. How did these gravitational monsters grow so unimaginably massive in what amounts to a cosmic heartbeat? For a black hole to reach 1 billion solar masses by the time the universe was just a toddler, it had to start with a significant head start. A stellar mass black hole, the kind formed from the collapse of a single massive star, simply cannot grow that fast through normal accretion. Even if it consumed gas at the maximum theoretically possible rate, a process known as Eddington-limited accretion, it would take far longer than a few 100 million years to reach such staggering proportions. It's like expecting a sapling to grow into a 1,000-year-old redwood tree in a single season. The math simply doesn't work, which means the initial seed for these supermassive black holes must have been something far more exotic than the remnant of a typical star. This puzzle has given rise to several compelling theories for the formation of these so-called black hole seeds. One of the leading contenders is the theory of direct collapse black holes. Imagine a pristine, massive cloud of primordial gas in the early universe, collapsing under its own gravity within a deep dark matter halo. Under normal circumstances, the gas would fragment into many smaller clumps, leading to the birth of a star cluster. But for a direct collapse to occur, a very specific condition must be met. The gas must be prevented from fragmenting. This could happen if the gas cloud is bathed in a powerful flux of ultraviolet light from a nearby, intensely star-forming galaxy. This intense radiation would destroy the molecular hydrogen within the cloud, which is the primary coolant for pristine gas. Without this efficient coolant, the gas cannot easily fragment. Instead, it undergoes a near-catastrophic monolithic collapse, funneling an enormous amount of material, tens of thousands or even hundreds of thousands of solar masses directly into a single massive object. This object wouldn't even have time to properly ignite as a star. It would collapse directly into a black hole, a seed that is already thousands of times more massive than any stellar remnant. This gargantuan seed provides the necessary head start, allowing it to subsequently grow through accretion to become a supermassive black hole within the available time. Another fascinating possibility involves the very first generation of stars, the population 3 stars. Some models suggest that under certain conditions, these stars could have grown to truly monstrous sizes, reaching up to 1 million solar masses. Such a supermassive star would be incredibly unstable, and after a brief life of just a few million years, it would collapse directly into a black hole without a supernova explosion, leaving behind a massive seed. Alternatively, in the dense environments of the first protogalaxies, runaway collisions and mergers of smaller stars could have created a single, supermassive object that would also collapse into a hefty black hole seed. Each of these pathways offers a different starting point, and astronomers are actively using observations to determine which mechanism was most prevalent in the early cosmos. But the seed is only half the story. The other half is the feeding frenzy. Once a massive seed is in place, it must consume gas at a ferocious and potentially super-Eddington rate to reach quasar proportions. This is where the host galaxy becomes absolutely critical. The host is not just a passive backdrop, it is the active feeding ground, the fuel depot that powers the quasar's brilliance. The key to rapid growth lies in the dynamics of the gas within these nascent galaxies. In the early universe, galaxies were much more gas-rich than they are today. Theories suggest that cold streams of gas flowing directly from the cosmic web along dark matter filaments could deliver vast amounts of cold, dense fuel directly to the galactic center, funneling it right into the waiting maw of the black hole. This continuous, high-density supply could allow for periods of hyperaccretion, where the black hole consumes gas far faster than the standard Eddington limit would allow. The host galaxy, in its turbulent, gas-rich youth, provides the perfect environment for such a feast, creating a powerful feedback loop where the infalling gas both feeds the black hole and is in turn heated and regulated by the black hole's intense radiation. This intimate connection is why finding and studying the host galaxies of these first quasars is one of the holy grails of modern astrophysics. It's an immense technical challenge, as the blinding glare of the quasar itself makes it incredibly difficult to see the faint, surrounding glow of the host galaxy's stars. It's like trying to discern the details of a candle flame while it's placed directly in front of a massive searchlight. However, with the advanced infrared capabilities and exquisite resolution of the James Webb Space Telescope, astronomers are now beginning to peel back the brilliant glare of the quasar to glimpse its host. What they are finding is revelatory. These hosts are not placid, stable systems. They are often massive, compact, and violently turbulent, undergoing enormous bursts of star formation. This supports the idea that the same processes that funnel gas to form stars at a tremendous rate, like the cold flow accretion and galactic collisions we've discussed, are also the very processes that deliver the vast reservoirs of fuel needed to power the central quasar. The growth of the black hole and the growth of the galaxy are two sides of the same coin, a co-evolutionary dance that began when the universe was in its infancy. By studying these first quasars and their hosts, we are witnessing the establishment of a relationship that would govern galactic evolution for billions of years to come. A partnership between star and void that shaped the cosmic landscape we see today. But for all the violent feedback occurring within individual galaxies, there is an even broader environmental force at work, a process that heats the cosmic landscape on the scale of entire clusters before a single galaxy has even fully formed. This is the theory of galaxy preheating, a large-scale mechanism that effectively sets the thermostat for future galactic growth across vast regions of space. To understand its power, we need to shift our perspective from the internal dynamics of a single galaxy to the colossal gravitational ballet of an assembling galaxy cluster. Imagine the primordial cosmic web, a network of dark matter filaments stretching across the universe. At the intersections of these filaments, where the gravitational pull is strongest, matter begins to flow inward, initiating the construction of a future galaxy cluster. This is not a gentle gathering, it is a chaotic and energetic collapse. As vast reservoirs of dark matter and gas fall into the growing gravitational well of the protocluster, they gain tremendous speed. When this infalling gas eventually collides with other streams of gas or encounters the growing potential well, it creates immense shock waves. These are not like sonic booms from an airplane. They are cosmic-scale tsunamis of energy that ripple through the intergalactic medium, heating the gas to temperatures of tens of millions of degrees. This is preheating. The gas is heated not by stars or black holes within galaxies, but by the sheer gravitational energy released during the assembly of the large-scale structure itself. The consequence of this early, widespread heating is profound. For a galaxy to form, the gas within a dark matter halo must be able to cool and condense. But if the gas entering the halo is already incredibly hot from this preheating process, it faces a much steeper uphill battle. The gas now has a much higher entropy, a measure of its disorder and heat content. High-entropy gas is puffy and resistant to compression. It's like trying to squeeze a hot, inflated balloon versus a cool, limp one. This makes it extremely difficult for the gas to cool down within the age of the universe. The preheating effectively raises the minimum mass a dark matter halo must have to be able to capture and cool gas to form a galaxy. Smaller halos with their weaker gravity are completely overwhelmed. They are starved before they even have a chance to begin, their potential fuel supply rendered too hot and energetic to capture. This theory provides an elegant solution to several puzzling observations about galaxy clusters. For instance, it explains the properties of the intracluster medium, the incredibly hot, diffuse plasma that fills the space between galaxies in a cluster. Simple models predicted this gas should have cooled significantly over billions of years, forming many more stars than we actually see. Preheating offers an explanation for why it remains so hot. Furthermore, it sheds light on the population of satellite dwarf galaxies. In the dense environment of a cluster, many of these small galaxies are devoid of gas and no longer forming stars, appearing as faint red relics. While processes like ram pressure stripping can explain this in the mature cluster, preheating suggests their fate may have been sealed much earlier during the cluster's violent birth. The gas they needed was heated globally, preventing them from ever achieving significant growth, leaving them as permanent fossils of a hostile upbringing. This large-scale environmental feedback demonstrates that a galaxy's destiny is shaped not only by its own internal processes, but by the energetic history of its entire neighborhood, a legacy of heat imprinted during the universe's most monumental construction projects. We've explored the colossal forces that shaped the early universe, from the violent mergers of galaxies to the invisible currents of dark matter. But there is another, more intimate legacy left by those first stars, one written not in gravity or light, but in the very atoms they created. This brings us to a theory that connects the life and death of the earliest stars directly to the chemical makeup of everything that followed. The profound impact of the first supernova on galaxy chemistry. The death of a population 3 star was not merely an endpoint. It was the moment the universe gained its periodic table, a transformative event that set the chemical course for future galaxies, planets, and even life itself. To appreciate the significance of this, we need to understand the concept of nucleosynthesis, the cosmic alchemy that forges new elements. During their brief, brilliant lives, massive stars like the population 3 giants act as immense nuclear furnaces. In their cores, under unimaginable temperatures and pressures, they fuse the primordial hydrogen and helium into heavier elements. This process happens in layered shells like the rings of a cosmic onion. At the center, hydrogen fuses into helium. In a shell around that, helium fuses into carbon and oxygen. Further out, carbon can fuse into neon, magnesium, and so on, all the way up to iron. Iron, however, is a nuclear dead end. Fusing iron atoms doesn't release energy, it consumes it. Once a star's core turns to iron, the energy production that has been supporting the star against its own gravity suddenly shuts off. This is the prelude to a supernova. With the core support gone, the star collapses catastrophically in a matter of seconds. The outer layers come crashing down onto the inert iron core at a significant fraction of the speed of light. The impact is so violent that it triggers a rebound shockwave, a titanic explosion that blasts the entire star apart. In this brief, inconceivably energetic inferno, conditions become even more extreme than in the star's core. A neutron-rich flood rushes through the exploding material, allowing for the rapid capture of neutrons, which builds elements heavier than iron like gold, silver, and uranium. In a few fleeting moments, a supernova can forge and scatter a vast array of elements across space. For the first time in cosmic history, the universe contained more than just hydrogen and helium. It was now seeded with carbon, oxygen, nitrogen, silicon, iron, and all the other fundamental ingredients for planets and life. But this story has a crucial twist. Population 3 supernova were not a uniform class. their final fates and thus their chemical legacies depended critically on their initial mass. A star on the lower end of the population 3 mass range, say around 25 to 40 times the mass of our Sun, would likely end its life in a relatively standard core collapse supernova. While immensely powerful, this explosion would still enrich the surrounding gas cloud with a significant yield of newly synthesized elements. This newly polluted gas would then collapse to form the next generation of stars, known as population 2 stars. These second-generation stars would therefore bear a distinct chemical signature. They would contain metals but at very low abundance. More importantly, their chemical pattern would be unique, reflecting the specific nuclear reactions that occurred inside that first massive star. However, for the very heaviest population 3 stars, those with masses soaring above 260 solar masses, the story takes a dramatically different turn. These behemoths are theorized to end their lives in a far more violent and complete explosion known as a pair instability supernova. In this scenario, the core becomes so hot that light itself begins to transform. Photons, the particles of light, can spontaneously convert into pairs of electrons and their antimatter counterparts, positrons. This conversion suddenly robs the core of the radiation pressure that was holding the star up. Without that support, the core undergoes a runaway collapse, leading to such intense thermonuclear burning that the entire star is completely obliterated. No black hole is left behind. Every bit of the star is vaporized and scattered into space. A pair instability supernova is so energetic that it can outshine an entire galaxy, and its chemical yield is immense, flooding the surroundings with a huge amount of heavy elements, particularly elements like oxygen and silicon. Then there is a third, darker path. For stars with masses between roughly 40 and 260 solar masses, the gravitational collapse may be so overwhelming that the entire star collapses directly into a black hole without a significant supernova explosion. In this scenario, the newly forged heavy elements, the products of the star's entire life of nuclear fusion, are not scattered into the cosmos. Instead, they are locked away forever behind the event horizon of the newborn black hole. This is a cosmic tragedy of sorts. A star that lived a brilliant life, creating a treasure trove of new elements, effectively takes its creations to the grave, leaving the surrounding gas cloud almost as pristine as it was before. A region dominated by such direct collapse black holes would be chemically starved, delaying the enrichment process and potentially leading to the formation of unusually metal-poor stars later on. This variation in supernova types created a patchwork of chemical enrichment across the early universe. Some regions were flooded with the ashes of a pair instability supernova, leading to second-generation stars with a very specific chemical fingerprint, an overabundance of certain elements like oxygen compared to iron. Other regions fertilized by a standard core collapse supernova would have a different pattern, and some areas remained chemical deserts, their gas still pristine because the first stars there had vanished into black holes. This means the oldest stars in our universe are living fossils, holding a record of the specific type of supernova that enriched the gas from which they formed. Astronomers are now engaged in a form of cosmic archaeology, using powerful telescopes to perform detailed chemical analyses of the most ancient stars in our own Milky Way halo. By measuring the precise ratios of elements like carbon, oxygen, magnesium, and iron in these ancient suns, they can work backwards, finding a star with a peculiar abundance pattern, such as a high ratio of oxygen to iron, could be the smoking gun for a pair instability supernova that occurred over 13 billion years ago. Each ancient star is a time capsule, preserving the chemical signature of a single, monumental death from the cosmic dawn, allowing us to read the autobiography of the first stars written in the elements they left behind. But as we attempt to peer ever deeper into the past, we confront a fundamental limitation of our technology: the extreme faintness of the earliest galaxies. Their light has traveled for over 13 billion years to reach us, stretched and dimmed by the relentless expansion of the universe. Even our most powerful telescopes, like the James Webb Space Telescope, have their limits. So how do we push beyond that observational frontier? Remarkably, nature itself provides a solution, a cosmic telescope built into the very fabric of space-time. This brings us to one of the most elegant and powerful tools in the modern cosmologist's arsenal, a phenomenon predicted by Einstein's theory of general relativity, gravitational lensing. The principle behind gravitational lensing is as beautiful as it is profound. Einstein revealed that mass warps the fabric of space-time. A massive object like a galaxy or a cluster of galaxies creates a kind of gravitational well, a depression in the cosmic landscape. Now imagine light from a distant galaxy traveling across the universe toward us. When this light passes near a massive foreground object, its path is no longer a straight line. It follows the curvature of space-time, bending as it travels through this gravitational well. It's analogous to how a glass lens bends light rays, focusing them to a point. A gravitational lens does the same thing, but using gravity instead of glass. This natural phenomenon comes in several forms. When a single, massive galaxy lies directly between us and a distant background galaxy, it can create multiple images of that background source, often stretched into bright arcs around the lensing galaxy. But the most powerful lenses of all are the massive clusters of galaxies. These colossal assemblies of dark matter, hot gas, and hundreds of galaxies create the deepest gravitational wells in the universe. When a distant, faint galaxy is positioned precisely behind such a cluster, the lensing effect is magnified dramatically. The cluster acts as a natural, cosmic zoom lens, bending and amplifying the light from the background object, making it appear dozens of times brighter and significantly magnified. This allows us to see galaxies that would otherwise be far too faint for any telescope to detect, effectively extending our vision to the very edge of observable time. However, the images we get are rarely clean and clear. The light from the background galaxy is not just magnified, it is often twisted and distorted into spectacular and bizarre shapes. Long, thin arcs, multiple smeared images, and even complete Einstein rings, where the galaxy appears as a perfect circle of light encircling the lensing cluster. To an untrained eye, these images might look like abstract cosmic art, but for astronomers, these distortions are not a problem. They are a treasure trove of information. The specific way the light is bent depends directly on the distribution of mass within the foreground lensing cluster, most of which is the invisible dark matter. So, by carefully mapping the distortions, theorists can create a precise model of the lens. They can essentially reverse engineer the gravitational field of the cluster. Once they have this detailed mass model, they can use it to reconstruct the true appearance of the background galaxy. It's a painstaking process of computational unraveling, but the results are breathtaking. This technique allows us to study the first galaxies with a level of detail that would otherwise be impossible. We can measure their physical size with incredible precision, resolving structures within them that are mere hundreds of light years across, even at these phenomenal distances. We can map out their star formation rates by analyzing their magnified light, and we can even begin to discern their internal structure, distinguishing between chaotic, clumpy protogalaxies and more ordered, rotating disks. Gravitational lensing has become indispensable in the quest to understand the cosmic dawn. It has allowed astronomers to confirm the existence of galaxies in the first few 100 million years after the Big Bang, objects whose light is so redshifted it has been stretched into the infrared part of the spectrum. By combining the magnifying power of these natural telescopes with the infrared sensitivity of the James Webb Space Telescope, we are now witnessing the formation of the very first galactic building blocks. This powerful synergy between a prediction of fundamental physics and cutting-edge technology is giving us an unprecedented front-row seat to the universe's earliest chapters, allowing us to watch the first lights turn on in the cosmic dark. Now, let's zoom in from the grand architecture of galaxies to the turbulent heart of the gas clouds themselves, where the actual business of star formation takes place. This brings us to a theory that focuses on the chaotic physics within these cosmic nurseries, the critical role of turbulence. We often picture a gas cloud collapsing under gravity in a smooth, orderly fashion, but the reality is far more violent and messy. Inside a proto-galaxy, the primordial gas was not a calm, static pool. It was a raging sea of chaotic, supersonic motion. This turbulence, these powerful, unpredictable currents and eddies churning through the gas, acted as a fundamental regulator, a cosmic puppet master controlling when, where, and how efficiently the first stars could be born. To understand why turbulence is so important, we need to think about the balance of forces within a gas cloud. On one side, you have gravity, which is relentlessly trying to pull the gas inward to make it collapse. Opposing gravity is pressure, which pushes outward, trying to keep the cloud puffed up. In a simple, quiet cloud, this balance determines its fate, but toss turbulence into the mix and everything changes. Turbulence is like adding a powerful, chaotic stir to the cloud. The swirling motions create regions of higher and lower density, and crucially, they generate a kind of turbulent pressure. This isn't the smooth, thermal pressure of a hot gas. It's a dynamic, rambling pressure that provides additional support against gravity's pull. A highly turbulent cloud can effectively hold itself up, resisting collapse for much longer than a calm one. This means that in the early universe, where other supporting forces like magnetic fields were weak, turbulence could have been the primary factor deciding whether a gas cloud fragmented into many stars or remained a single, quiescent entity. However, turbulence has a dual nature. While its overall effect can be to support a cloud against global collapse, it also creates the very seeds for star formation on smaller scales. As these supersonic motions crash into one another, they create powerful shock waves. Imagine two mighty ocean waves colliding head-on. The water at the point of impact is violently compressed. In a gas cloud, these turbulent shocks do the same thing, squeezing the gas into incredibly dense filaments and knots. Within these localized, high-density regions, gravity can suddenly gain the upper hand over the local pressure. A cloud that is too turbulent to collapse as a whole can still fragment into numerous dense cores, each one a potential site for a single star or a small stellar system to form. So, turbulence doesn't just prevent collapse, it also orchestrates it, carving the cloud into the specific fragments that will eventually ignite. The sources of this primordial turbulence were numerous and powerful. One major driver was the continuous inflow of gas from the cosmic web. As cold streams of pristine hydrogen and helium flowed along the dark matter filaments and poured into the growing proto-galaxy, they didn't arrive smoothly. These streams collided with each other and with gas already in the halo, creating a cacophony of shocks and chaotic motions that stirred the entire system. Another potent source was feedback from the first stars themselves. Even as a massive star was forming, its intense radiation would begin to heat and ionize the surrounding gas, causing it to expand violently and stir up the nursery. And when it died as a supernova, the blast wave would inject an enormous amount of kinetic energy, like a colossal paddle churning the gas, generating turbulence that could either trigger new star formation in compressed shells or disrupt other nascent clouds entirely. Galactic mergers, of course, were the ultimate turbulence generators, their gravitational tides violently shaking the gas disks and creating widespread, intense disorder. The efficiency of the very first starburst likely hinged on the precise level of this turbulence. If it was too low, gas could collapse too readily, perhaps forming a few overly massive stars. If it was too high, star formation might be suppressed entirely, as the cloud remained too stirred up to condense. Theorists believe there may have been a sweet spot where turbulence was strong enough to promote widespread fragmentation, leading to the efficient formation of a full spectrum of star sizes, but not so strong as to completely tear the cloud apart. Modeling this delicate balance is one of the greatest challenges in simulating the early universe. By incorporating the physics of supersonic turbulence into their sophisticated computer models, astrophysicists are beginning to recreate the chaotic conditions within those first protogalaxies, helping us understand how the intricate dance between chaos and gravity gave rise to the universe's initial population of stars. However, for all the remarkable success of the lambda-CDM model in explaining the universe on the largest scales, it faces a persistent and significant challenge when we zoom in to examine our own cosmic neighborhood. This is the notorious satellite galaxy problem, a puzzle that pits the pristine predictions of supercomputer simulations against the messy reality of our telescopic observations. The heart of the discrepancy is both simple and profound. According to the hierarchical model, large galaxies like our Milky Way were built from the mergers of countless smaller protogalaxies. The dark matter halos of these giant galaxies are not smooth. They are filled with a vast swarm of smaller subhalos, the leftover building blocks that were gravitationally captured but never fully assimilated. Sophisticated simulations consistently show that a halo the size of the Milky Ways should be teeming with many thousands of these dark matter clumps. Yet, when we look up at the sky and count the satellite galaxies orbiting our own, we find only a few dozen. It is a staggering mismatch, a prediction of thousands set against an observation of merely a few dozen. Where are all the missing satellites? This isn't just a minor accounting error. It strikes at the very heart of our understanding of how structure forms. If the simulations are correct, then there must be a compelling reason why the vast majority of those dark matter subhalos failed to light up with stars and become visible galaxies. One of the most promising solutions brings us back to the transformative power of the epoch of reionization. Imagine one of these small, pristine subhalos in the early universe. It begins to attract a wisp of hydrogen gas, poised to potentially form the first generation of stars. But then, the cosmic horizon begins to brighten as the first galaxies and quasars ignite. A flood of ultraviolet radiation sweeps across the cosmos, heating the intergalactic medium. For a small halo with a shallow gravitational well, this external heating is a catastrophe. The intense radiation either evaporates its gas entirely or heats it to such a high temperature that it becomes impossible for the weak gravity of the halo to hold onto it. The subhalo is left intact, a perfectly good clump of dark matter, but it has been stripped of its baryonic fuel. It becomes a dark galaxy, a ghost of gravitational potential entirely devoid of stars. In this scenario, the simulations are right about the dark matter, but our observations are naturally limited to the small fraction of subhalos that were either massive enough to withstand the blast or that accreted their gas after the worst of the reionization era had passed. Another possibility is that our census of the Milky Way's satellites is simply incomplete. For decades, our searches were limited, only able to detect the relatively bright classic dwarf spheroidal galaxies like Fornax and Sculptor. But in recent years, with the advent of powerful digital sky surveys, astronomers have discovered a whole new population of ultra-faint dwarf galaxies. These are incredibly ghostly objects, so diffuse that they can be hiding in plain sight, their few thousand stars blending seamlessly into the foreground of our own galaxy's stellar disk. The discovery of these ultra-faint dwarfs has already dramatically increased the satellite count. It is entirely plausible that even fainter, more dark matter-dominated satellites are still lurking undetected in the halo, just at the edge of our observational capabilities. The Vera C. Rubin Observatory, set to begin operations soon, is specifically designed to conduct an ultra-deep survey of the entire sky, and it is expected to find hundreds, if not thousands, of these incredibly faint systems. It may well be that the satellite problem is, at least in part, a problem of observational limits, and that the coming decade will see the gap between theory and observation narrow significantly. A more radical line of inquiry questions the very nature of dark matter itself. The predictions of thousands of superhalos are based on the assumption that dark matter is cold, meaning the particles are slow-moving. But what if dark matter is slightly warm with particles that are lighter and faster? Warm dark matter would have a profound effect. Those fast-moving particles would have smoothed out the smallest density fluctuations in the early universe. This would prevent the formation of the very tiniest dark matter superhalos, starting the hierarchy of structure at a larger mass scale. In a warm dark matter universe, the number of small superhalos predicted to orbit a galaxy like the Milky Way would be drastically reduced, potentially bringing the theory into much closer alignment with the observed count of satellite galaxies. While the evidence still strongly favors cold dark matter, the satellite problem keeps the door open for these exotic alternatives, making it a fertile testing ground for fundamental physics. This ongoing tension is not a weakness of cosmology, but rather a sign of a healthy, active field. It forces scientists to refine their models, to push the limits of observation, and to think creatively about the intricate interplay between dark matter, gas physics, and the cosmic environment. The search for the missing satellites is ultimately a quest to understand the complete ecosystem of our galaxy, from its brightest stars to its darkest, most elusive shadows. The hunt for these dark galaxies pushes observational astronomy to its absolute limits, demanding techniques far beyond simply pointing a telescope at a dark patch of sky and taking a picture. Since these objects emit almost no starlight, astronomers have to become cosmic detectives, searching for indirect clues that betray their presence. One of the most promising methods involves listening for a specific, faint radio whisper, the 21-centimeter line of neutral hydrogen. Neutral hydrogen gas, even when it isn't collapsing to form stars, has a tiny, inherent energy transition. Occasionally, the electron in a hydrogen atom will flip its spin, and when it does, it emits a photon with a wavelength of 21 centimeters, which falls in the radio part of the spectrum. If a dark galaxy contains a reservoir of this primordial gas, it should be emitting this signature, albeit incredibly faintly. Radio telescopes like the Low-Frequency Array, or LOFAR, are designed to scan the skies for this specific signal, hoping to pick up the faint glow of hydrogen from dark matter halos that have never known the light of stars. The challenge is monumental, as the signal is not only weak but also stretched to longer wavelengths by the expansion of the universe, making it even harder to detect. Another ingenious approach uses the ambient light of the cosmos itself as a flashlight. After the epoch of reionization, the universe was filled with a diffuse background of ultraviolet radiation, the combined glow of every galaxy and quasar that has ever existed. When this ultraviolet light encounters a cloud of neutral hydrogen, like the one that might surround a dark galaxy, it can excite the atoms, causing them to fluoresce. This is a process known as fluorescence, similar to how a blacklight causes certain paints to glow. The resulting emission is extremely faint, but in theory, it could create a detectable, extended halo of ultraviolet light around a dark matter halo. Searching for this ghostly fluorescence requires incredibly sensitive space-based telescopes and painstaking analysis to distinguish it from the foreground glare of our own galaxy and other background sources. It's like trying to see the faint glow of a jellyfish in the deep sea using only the dim, scattered sunlight from the surface. Gravitational lensing, our powerful cosmic magnifying glass, also offers a way to probe the existence of dark galaxies. If a dark matter halo devoid of stars passes directly between us and a more distant, bright galaxy, its gravity will still bend the light from the background source. This can create subtle but measurable distortions in the shape of the background galaxy, even if the lens itself is completely invisible. By meticulously analyzing the shapes of thousands of distant galaxies, astronomers can map the distribution of intervening mass, including clumps that have no associated starlight. These weak lensing surveys have indeed found tantalizing anomalies, regions where the gravity seems to suggest a concentration of mass that is not marked by any visible galaxy. While these detections are still controversial and difficult to confirm, they represent some of the most direct evidence for the presence of dark matter halos that fit the description of a true dark galaxy. The potential discovery of a confirmed dark galaxy would be a monumental breakthrough, far more than just solving the satellite problem. It would provide a pristine laboratory for studying dark matter in isolation, free from the complicating effects of stars and energetic feedback. By measuring the rotation of the gas within a dark galaxy, for instance, astronomers could chart the distribution of dark matter with unprecedented precision, testing the fundamental predictions of how dark matter halos are structured. Furthermore, finding these objects would powerfully confirm the narrative that reionization was a pivotal environmental event that shaped the population of galaxies we see today. It would mean that for every brilliant spiral like the Milky Way, there could be dozens, hundreds, or even thousands of dark counterparts, silent, ghostly islands of dark matter and primordial gas, drifting through the cosmic night as permanent relics of a time when the universe first began to turn on the lights. But this intricate relationship between a galaxy's observable properties and its underlying dark matter halo has an even deeper layer of complexity, one that challenges a fundamental assumption in our models. We've seen how galaxy biasing means that bright galaxies prefer to live in dense neighborhoods, tracing the peaks of the dark matter distribution. This has led to a convenient and powerful simplification, that the properties of a dark matter halo are determined primarily by a single number, its mass. The idea is that if you know the mass of a halo, you can predict, on average, how it will cluster with other halos and what kind of galaxy it might host. This is the cornerstone of connecting theory to observation. However, a fascinating and more nuanced theory, known as galaxy assembly bias, suggests that mass alone does not tell the whole story. The history of a halo, specifically when it formed, can leave an indelible mark on its place in the cosmic web, independent of its size. The core idea of assembly bias is elegantly simple, yet its implications are profound. It proposes that two dark matter halos with exactly the same mass in the present-day universe might not cluster in the same way if they assembled at different times in cosmic history. An ancient halo, one that formed its core structure very early on, might have a stronger tendency to reside in the densest environments, like the rich clusters at the intersections of filaments. Meanwhile, a halo of identical mass that formed more recently might be found in a more average environment, perhaps along a filament but not at its busiest nexus. This means that the formation history, or the age, of a halo is an additional, independent factor that influences where it ends up. It's not just about how big you are, it's also about when you grew up. To understand why this might happen, we need to think about how the cosmic web itself develops. In the hierarchical model, the first structures to collapse are the peaks of the primordial density field, the regions that were slightly denser than average from the very beginning. Gravity works fastest in these regions, pulling matter together rapidly. Therefore, the halos that form earliest are born in the most overdense environments, the future nodes of the cosmic web. As the universe expands and evolves, gravity pulls matter from the surrounding underdense regions into the growing filaments and clusters. Halos that form later do so from material that originated in these less dense surroundings. They are relative latecomers to the cosmic metropolis. So, even if a late-forming halo eventually gathers the same amount of mass as an early-forming one, its address within the large-scale structure might still reflect its more humble origins. The early forming halo is a native of the big city, while the late forming halo is a recent arrival who has acquired wealth but may not yet live in the most exclusive neighborhood. This subtle effect has significant consequences for how we interpret our maps of the universe. If assembly bias is a real and important phenomenon, then our standard methods of connecting galaxies to dark matter could be missing a crucial piece of the puzzle. For decades, astronomers have used the observed clustering of galaxies to measure fundamental properties of the universe, like the overall amount of matter and the nature of dark energy. These measurements rely on the assumption that galaxy clustering reliably traces mass clustering. But if the clustering strength depends not only on halo mass but also on halo age, then our interpretations could be biased. We might be misreading the cosmic map. For example, if older, red, dead elliptical galaxies preferentially reside in older halos that cluster more strongly, and younger, star-forming spiral galaxies live in younger halos that cluster more weakly, the observed galaxy distribution would appear more clustered than the underlying dark matter distribution truly is. Failing to account for this could lead to incorrect estimates of cosmological parameters. The most exciting implication of assembly bias, however, is its potential as a powerful test for different models of dark matter. The strength and specific signature of assembly bias are predicted to be different for cold dark matter versus warmer, more exotic alternatives. In the cold dark matter model, which allows for structure to form on very small scales early on, the effect of assembly bias is expected to be relatively modest but detectable in sophisticated simulations. In a warm dark matter universe where the earliest small-scale structures are suppressed, the formation history of halos would be different, potentially imprinting a distinct signature on their clustering patterns. Therefore, by meticulously measuring the clustering of galaxies of different types and ages, astronomers can hunt for the specific fingerprints of assembly bias. Finding a clear signal that matches the predictions of cold dark matter would be a strong confirmation of our standard model. Conversely, detecting a deviation could point toward new physics, suggesting that dark matter particles have properties we have not yet anticipated. This transforms the large-scale structure of the universe from a simple outcome of gravity into a rich archaeological record, where the spatial distribution of galaxies encodes not only the amount of dark matter, but also its fundamental nature and the detailed timeline of cosmic assembly. This brings us to a dimension of cosmic evolution that is less about a galaxy's internal properties and more about its cosmic zip code. The theory of large-scale environmental influence posits that a galaxy's destiny is profoundly shaped by its neighborhood within the vast architecture of the universe. Just as a plant growing in a dense, competitive rainforest follows a different life path than one in an isolated desert, a galaxy's evolutionary journey is dictated by whether it resides in a bustling metropolitan cluster or a quiet, rural void. This cosmic environment acts as an overarching selective pressure, determining which galaxies will thrive, which will transform, and which will see their star-forming lives cut short. The most extreme environments are the rich galaxy clusters, the megalopolises of the cosmos. These are immense gravitational wells containing hundreds or even thousands of galaxies, all bathed in a searingly hot plasma known as the intracluster medium. For a spiral galaxy rich with cold gas, the fuel for new stars falling into one of these clusters is a perilous journey. As the galaxy plunges through this thin but incredibly hot intergalactic gas at speeds of millions of kilometers per hour, it experiences a phenomenon called ram pressure stripping. The analogy is like sticking your hand out of the window of a moving car. The force of the wind pushes against you. For the galaxy, the wind is the intracluster medium. The force of this impact is so powerful that it can literally blow the galaxy's own gas right out of its disk. Since the stars are much more tightly bound by gravity, they remain largely unaffected. But the loose clouds of atomic and molecular hydrogen, the raw material for future generations of stars, are swept away as if by a cosmic broom. the galaxy is effectively robbed of its future, its star formation quenched as it becomes a gas-poor, red and dead relic. We see this dramatic evidence in clusters like Virgo, where spiral galaxies appear to have their gas tails stretched out behind them like comets streaking through space. Beyond this violent gas stripping, galaxies in dense clusters also suffer from a more subtle but equally destructive process known as galaxy harassment. In the crowded core of a cluster, galaxies frequently zip past each other at high speeds. These are not the slow, merging embraces we discussed earlier, but rapid flyby encounters. Each close passage exerts a gravitational tug that subtly distorts the galaxies, puffing up their stellar disks and disrupting their delicate structures. Repeated over billions of years, this harassment can effectively tear a spiral galaxy apart, randomizing the orbits of its stars and transforming it from an ordered, rotating disk into a more featureless, elliptical-shaped galaxy. It's a death by 1,000 gravitational cuts. Furthermore, the immense tidal force of the cluster's overall gravitational field can also strip away a galaxy's outermost stars and any small satellite galaxies it may have had, slowly eroding its identity. In stark contrast, consider the galaxies that inhabit the cosmic voids, the vast, empty spaces between the filaments of the cosmic web. These isolated galaxies lead profoundly different lives. Free from the oppressive heat and gravitational turbulence of clusters, they evolve in a comparatively gentle environment. They can hold onto their gas reservoirs for much longer, and their peaceful existence allows for steady, sustained star formation. These void galaxies are often gas-rich, irregular, and bluer in color, signifying ongoing stellar birth. They are the cosmic equivalent of a small town with a slow, steady economy, untouched by the booms and busts of the big city. Their evolution is driven primarily by their internal processes, like the fuel they consume and the feedback from their own stars, rather than the brutal external pressures that dominate cluster life. When we apply this environmental perspective to the very first galaxies, it adds a crucial layer to their origin story. Those pioneering structures almost certainly did not form within the dense, violent environments of modern-day clusters. The first proto-galaxies assembled in relatively average regions of the early cosmic web, growing in isolation or within small groups. Their initial development was governed by their own internal physics, the efficiency of their first starbursts, the growth of their central black holes, and their own minor mergers. However, their long-term fate was already written in the gravitational landscape. The inexorable pull of gravity meant that these galaxies and their descendants were destined to be drawn toward the growing nodes of the cosmic web. Over billions of years, they were funneled along the dark matter filaments, eventually falling into the massive clusters that were assembling at the intersections. The story of galaxy evolution is therefore not just one of birth, but also of migration. A galaxy could be born in a quiet void, live a vigorous youth of star formation, only to have its life radically altered when it moved to the dense urban core of a cluster, where environmental forces stripped it of its gas and transformed its very shape. This grand narrative connects the intimate physics of star formation to the largest structures in the universe, showing that a galaxy's history is an inseparable blend of its inherent nature and the nurture provided by its cosmic environment. But if we wish to move beyond the fossilized remnants of the cosmic dawn and truly watch the universe wake up in real time, we need a method that can pierce the veil of those first few 100 million years with unprecedented clarity. This brings us to a theory that is less about what happened and more about how we will finally see it happen, a revolutionary observational technique that promises to turn the entire early universe into a celestial movie screen. This is the potential of the 21-centimeter signal, a faint radio whisper that holds the key to producing a direct, three-dimensional map of the universe's transformation from darkness to light. The principle behind this signal is as elegant as it is powerful. It relies on a tiny, fundamental property of the neutral hydrogen atom, the most abundant substance in the early cosmos. In its ground state, the single electron and the single proton that make up a hydrogen atom can spin in two possible configurations, aligned or anti-aligned. The anti-aligned state has a slightly higher energy. Very occasionally, an atom in the higher energy state will spontaneously flip, and when it does, it releases the tiny energy difference as a photon with a very specific wavelength, 21 centimeters, which lies in the radio part of the electromagnetic spectrum. For any single atom, this event is incredibly rare, happening on average only once every 10 million years or so. But when you have a universe filled with countless trillions of hydrogen atoms, this rare event becomes a constant, faint chorus. The entire neutral universe hums with this 21 centimeter radiation. The true power of this signal, however, lies not in its mere presence but in how it changes. The wavelength of this emission is not fixed. It is stretched by the expansion of the universe, a phenomenon known as redshift. The further away the hydrogen cloud is, the more the light is stretched. This means that by tuning our radio telescopes to different wavelengths, we are effectively tuning into different slices of cosmic time. A signal detected at a wavelength of 2 meters, for instance, corresponds to hydrogen from an earlier epoch than a signal at 1 meter. This allows astronomers to create a three-dimensional tomographic map of the distribution of neutral hydrogen throughout the history of the universe. We can slice the cosmos like a loaf of bread, examining each layer in turn. Now apply this to the epoch of the first galaxies. Before any stars ignited, the universe was a vast cold sea of neutral hydrogen. This gas would have been emitting its 21 centimeter signal unimpeded. But then, the first sources of light began to switch on. The ultraviolet radiation from these first stars and galaxies did two things to the surrounding hydrogen gas. First, it heated the gas. Second, and more dramatically, it ionized the gas, ripping the electrons away from the protons. Ionized hydrogen cannot produce the 21 centimeter signal at all. So, as the era of reionization progressed, the universe transformed from a brilliant emitter of 21 centimeter radiation into a silent void, at least at this specific frequency. The crucial point is that this didn't happen uniformly. The first ionizing sources created growing bubbles of transparency, spheres of ionized gas within the neutral hydrogen fog. As these bubbles expanded and overlapped, the 21 centimeter signal would have gradually faded from the inside out. This is where the promise of a true cosmic movie comes in. By mapping the subtle variations in the strength of the 21 centimeter signal across the sky and at different redshifts, we could effectively watch these ionized bubbles appear, grow, and merge. It would be like watching ice melt on a lake in reverse. Instead of patches of water appearing in a sheet of ice, we would see patches of silence, regions where the 21 centimeter signal vanishes, appearing and spreading through a noisy background. This would provide a direct dynamic view of reionization, allowing us to answer fundamental questions. Did reionization start with a few brilliant, isolated quasars? Or was it a more democratic process driven by a vast population of small, faint galaxies? How long did the entire process take? The 21 centimeter signal holds the answers. Capturing this signal, however, is one of the most formidable challenges in modern observational astronomy. The radiation is incredibly faint, and it is redshifted into the low-frequency radio band, which is notoriously polluted by human-made interference from everything from FM radio stations to satellite transmissions. Furthermore, the signal is overwhelmed by foreground emissions from our own galaxy and other astrophysical sources that are millions of times brighter. Separating the cosmic dawn signal from this cacophony is like trying to hear a pin drop in the middle of a hurricane. It requires telescopes of unprecedented scale and sensitivity, along with sophisticated computer algorithms to digitally remove the foregrounds. This is the monumental goal of next-generation projects like the Square Kilometre Array or SCAR. When completed, the SKA will be the largest radio telescope ever built, comprising thousands of antennae spread across 2 continents, South Africa and Australia. Its collective power will provide the sensitivity and resolution needed to finally tune into the universe's earliest channels and produce the first ever map of the cosmic dawn. The detection of this signal will not just be a technical achievement. It will open an entirely new window on the first billion years, transforming our understanding of cosmic beginnings from a series of static snapshots into a breathtaking, full-motion picture of creation itself. For all the power and elegance of the lambda cold dark matter model, its entire framework rests upon an invisible substance we have never directly detected. This dependency has led a small but persistent group of physicists to propose a radically different solution, one that challenges the very laws of physics as we know them. What if the problem isn't a missing ingredient but a flaw in the recipe itself? This is the bold proposition of alternative gravity theories, most notably modified Newtonian dynamics or MN. Instead of invoking vast halos of dark matter to explain why galaxies don't fly apart, MN suggests that our understanding of gravity is simply incomplete, and that on the immense scales of galaxies, gravity behaves differently than Isaac Newton or even Albert Einstein predicted. The central puzzle that MN seeks to solve is the galaxy rotation curve problem, which we encountered at the very beginning of our journey. According to Newton's law of gravity, stars and gas clouds orbiting the center of a galaxy should move slower the further out they are, just as Pluto orbits the Sun much more slowly than Mercury does. But observations since the 1970s have consistently shown that rotation speeds remain flat or even increase far out into the galactic outskirts. The dark matter solution is to add an invisible mass that provides the extra gravitational glue. MUND, proposed by physicist Mordechai Milgrom in the 1980s, offers a more minimalist fix. It introduces a simple modification. When the gravitational acceleration becomes incredibly weak, as it does in the sparse outer regions of galaxies, the force of gravity stops following the familiar inverse square law and instead becomes stronger. This tiny adjustment, triggered at accelerations billions of times weaker than what we feel on Earth, mathematically predicts those flat rotation curves with striking accuracy, all without a single particle of dark matter. Applying this idea to the formation of the first galaxies, however, requires a complete reimagining of the cosmic blueprint. Without dark matter halos to act as gravitational anchors, how did structure form in the early universe? Proponents of MUND and its relativistic extensions like TVS have developed alternative scenarios. In these models, the initial seeds for galaxy formation wouldn't be quantum fluctuations amplified by cold dark matter. Instead, the focus shifts to the behavior of the normal, baryonic matter, the hydrogen and helium gas under the modified rules of gravity. The theory suggests that in a MONDIAN universe, gravitational instability could occur more rapidly and efficiently on the scales of galaxies. The enhanced gravity in low acceleration regimes might have allowed protogalactic gas clouds to collapse directly into galaxies without needing the prior assembly of a dark matter scaffold. This could potentially lead to galaxies forming earlier and through a more monolithic process than the hierarchical merging we see in the standard model. The debate between these two paradigms is a fascinating example of how science progresses through confrontation. Supporters of MUND point to its remarkable success in explaining the detailed dynamics of individual galaxies with fewer free parameters than dark matter models, which often require complex halo profiles to fit observations. They argue that MUND is an elegant solution that does away with the need for a mysterious, undiscovered substance. However, the model faces significant challenges, especially when confronted with evidence from larger scales. The Bullet Cluster, a system of 2 colliding galaxy clusters, provides a powerful case study. observations show that the mass of the clusters, mapped through the gravitational lensing of background galaxies, is separated from the visible matter. The X-ray emitting gas, which constitutes most of the normal matter, lags behind because it experiences a drag force, while the mass which we attribute to dark matter has sailed right through. In a pure framework without some form of additional matter, it is extremely difficult to explain why the gravitational field isn't centered on the visible mass. This strongly suggests that there is, in fact, a form of matter that does not interact with light. Furthermore, the precise pattern of fluctuations in the cosmic microwave background and the large-scale structure of the cosmic web are beautifully explained by the lambda-CDM model with dark matter, while reproducing these features with modified gravity alone has proven to be a formidable task. The true value of theories like MUND may not lie in replacing dark matter, but in the profound questions they force the mainstream to answer. They act as a necessary gadfly, compelling cosmologists to rigorously test the dark matter paradigm and to seek definitive evidence. The ongoing tension has led to innovative searches for dark matter particles and to more sophisticated computer simulations that can make testable predictions about galaxy formation. It has also inspired hybrid ideas, such as the possibility that both modified gravity and some form of dark matter could be part of the ultimate story. This vibrant debate underscores a fundamental principle of science. Our models are not perfect, and the path to understanding the cosmos is paved with challenges to conventional wisdom. Whether MUND itself is ultimately validated or not, its existence ensures that our quest to comprehend the universe's first galaxies remains a dynamic, critical, and deeply creative endeavor. And so, our journey through 30 theories brings us full circle, from a formless, silent cosmos to the magnificent, structured universe we are privileged to observe. We have witnessed the invisible hand of dark matter laying the gravitational groundwork, the torrential cold flows of pristine gas fueling a frantic adolescence of star birth, and the explosive feedback from brilliant stars and ravenous black holes that both ignited and quenched galactic growth. This story is not one of a single triumphant theory, but a grand symphony of interwoven processes. Gravity provided the irresistible pull, dark matter the unseen framework, and the complex physics of gas, its cooling, its turbulence, its chemistry provided the raw material and the rules of engagement. It is in the dynamic tension between construction and destruction, between the pull of gravity and the push of radiation, that the beautiful diversity of galaxies was forged. This entire narrative, once confined to the realm of theoretical models and computer simulations, is now being brought into stunning reality by a new generation of observatories. The James Webb Space Telescope is acting as a time machine, its infrared eyes peering back to an era when the first starlight was just beginning to pierce the darkness. With each deep field image, with every spectrum of a 13-billion-year-old galaxy, Webb is providing crucial data that tests our boldest ideas. It is searching for the faint, clumpy structures predicted by hierarchical models, analyzing the light of ancient stars to find the chemical signature of the first supernova, and hunting for the seeds of supermassive black holes. We are no longer just imagining the cosmic dawn. We are starting to witness it, with each new observation refining our understanding and often presenting us with surprising puzzles that push our theories to their limits. Yet for all we have learned, the story is far from complete. The true nature of dark matter remains one of the greatest mysteries in physics. Were the very first stars indeed monstrous giants? And if so, why have we not yet definitively found their descendants? How exactly did the first black holes grow so massive, so quickly? The upcoming era of observation, with instruments like the Vera C. Rubin Observatory and the Square Kilometre Array, promises to probe these questions with even greater depth. They will census millions of galaxies to map the cosmic web in exquisite detail, and may even detect the faint radio hum of the universe's hydrogen before the first stars turned on. The adventure of discovery is accelerating, and the next decade will undoubtedly rewrite chapters of the story we have just begun to tell. This incredible quest to understand our own origins by studying the birth of galaxies is a testament to human curiosity. We have pieced together this history from the faintest whispers of light using the laws of physics as our guide, and now we want to hear from you. After exploring these 30 theories, from cosmic inflation and hierarchical clustering to tidal dwarfs and modified gravity, which idea captivates your imagination the most? Do you find the silent dominance of dark matter the most profound, or is it the cataclysmic lives and deaths of the first stars that resonates with you? Share your thoughts in the comments below, and let's continue this conversation about the greatest story ever told, the story of how our universe grew from darkness